Hello there and welcome to Science for Sleep, where curiosity drifts softly through the universe and the quiet hum of discovery helps the mind settle into rest. Tonight, our gentle voyage takes us far beyond the edges of ordinary imagination into a place so vast, so deep, that even light itself cannot return from it. Somewhere out there, in a galaxy cluster known as Phoenix, lies a black hole so massive that the usual words fail to describe it. It is called Phoenix A, and it may be the largest black hole ever found in the observable universe. Its presence bends not only the fabric of space, but also the boundaries of what we think is possible. Before we begin to unravel the story of this colossal being, I wonder where you are listening from tonight. Maybe you're in a city where the glow of streetlights fades just enough for one or two stars to peek through, or maybe you're somewhere quiet, far from the noise, where the Milky Way arches above like a pale river. Wherever you are, imagine looking up and realizing that somewhere among those faint dots of light lies a place so enormous, so dense, that it anchors an entire cluster of galaxies around it. If you find comfort in these quiet explorations of the cosmos, if you enjoy learning about the mysteries of space while the world slows down, a like or a small tap on subscribe would help this calm corner of science find others who might need a peaceful moment too. But for now, there's no hurry. Just settle in, let your breathing slow, and let's drift together toward a region of the universe where gravity rules with absolute authority. The story of Phoenix A begins not with fire, but with silence. It sits in the heart of the Phoenix cluster, a collection of galaxies so distant that its light has travelled nearly 6 billion years to reach us. When we look at it through the powerful eyes of space telescopes, we are seeing it as it was when the universe was roughly half its current age. Even from that incomprehensible distance, the signs of something extraordinary stand out. Radio waves and X-rays pour from its centre, evidence of a cosmic engine of staggering power. In visible light, the cluster appears as a loose gathering of galaxies, each glowing softly like scattered embers. But behind that peaceful image lies violence on a scale our minds can barely contain. Black holes come in different sizes, from the tiny remnants of collapsed stars to the supermassive ones that sit at the centres of galaxies. Phoenix A belongs to the uppermost tier of this hierarchy, a class so extreme that astronomers had to rethink their understanding of how such things could form. Its estimated mass is about 100 billion times that of our Sun. To put that in perspective, if the black hole at the centre of our Milky Way, Sagittarius A, were the size of an orange, Phoenix A would be roughly the size of a house. It is not merely a point in space. It is a gravitational domain, an invisible monarch ruling over billions of stars. What makes this black hole so remarkable isn't only its size, but also the company it keeps. The Phoenix cluster is a particularly dense region of the universe, filled with hot gas, ancient stars, and smaller galaxies orbiting like bees around a hive. In the cluster's centre lies a massive galaxy, known simply as the brightest cluster galaxy. It's within this luminous host that Phoenix A resides, quietly influencing the fate of everything around it. When astronomers point their instruments toward this region, they find immense cavities carved into the surrounding gas. These are not empty spaces in the usual sense, but regions where the black hole's jets have blasted material outward, pushing back against the dense plasma that fills the cluster. The scale of this activity defies easy comparison. Each of those cavities could contain entire galaxies. The energy released is equivalent to hundreds of millions of supernovae exploding simultaneously. And yet, the astonishing thing about Phoenix A is that even this ferocity is part of a kind of balance. Black holes do not merely consume, they also regulate. The heat and radiation they generate can slow or even halt the formation of new stars by preventing gas from cooling and collapsing. Without such feedback, clusters like Phoenix might produce stars too quickly, burning through their raw material and leaving nothing behind but cold emptiness. In a strange way, these monsters act as cosmic thermostats, maintaining a delicate equilibrium that allows galaxies to persist for billions of years. The Phoenix cluster is a vivid example of this process in action, where destruction and preservation are intertwined. When the cluster was first studied in detail, astronomers noticed something curious. The central galaxy was forming stars at an unusually high rate, far more than what is typical for clusters of its kind. This suggested that the feedback from the black hole was temporarily weaker or had changed in some way, allowing cool gas to condense and ignite new stellar nurseries. Some even speculated that Phoenix A had entered a quieter phase, taking a break from its usual violence, though the marks of its past outbursts still linger across the cluster like scars in the cosmic fabric. Observations across multiple wavelengths, X-ray, optical, radio, help piece together this story. The Chandra X-ray Observatory reveals the searing hot gas that fills the cluster, glowing with temperatures of tens of millions of degrees. Radio telescopes, like those at the Very Large Array, detect the faint hum of synchrotron radiation produced by charged particles spiraling through magnetic fields, a telltale sign of relativistic jets. Combined, these observations create a portrait of Phoenix A as both ancient and active, a being whose existence spans cosmic epochs. It's tempting to imagine black holes as simple voids, but that's far from the truth. Around the event horizon, the boundary beyond which nothing can escape, matter whirls at nearly the speed of light. As it falls inward, friction and magnetic turbulence generate temperatures hotter than any stellar surface. This energy radiates outward, creating brilliant accretion disks that can outshine entire galaxies. Phoenix A, with its immense mass, has a gravitational pull so deep that even photons struggle to climb free. The light that does escape comes from the turbulent disk just outside the horizon, where matter is shredded into radiation before disappearing forever. There's a certain quiet awe in realizing that something invisible, something that emits no light of its own, can shape the structure of galaxies and the fate of stars. Black holes like Phoenix A are not rare, but this one is exceptional for its scale. It sits near the upper limit of what theory allows. If it grew much larger, its own gravity would start to trap the radiation that feeds it, effectively limiting its further growth. This self-regulation may be one reason such enormous black holes are so rare. Still, the existence of Phoenix A challenges models of how black holes form and evolve. To reach 100 billion solar masses, it must have begun as an enormous seed, perhaps a direct collapse black hole formed from clouds of primordial gas in the early universe, rather than from the remnants of the first stars. Tracing that history is like following a whisper through billions of years. The light we see now began its journey when Earth was still forming its first complex life. Every photon that reaches our telescopes carries information from that ancient past. In studying Phoenix A, astronomers are not merely observing an object, they are peering back through cosmic history, reconstructing how galaxies and clusters have changed over time. The deeper we look, the more we realize how connected everything is. The birth of a star, the death of a galaxy, the quiet hunger of a black hole. These are not separate events, but threads in one continuous tapestry. When you think about it, there's a strange serenity in the concept of a black hole. From a distance, it seems almost still, unchanging, eternal. Up close, it is chaos and motion and collapse. Yet both are true. The immense gravitational field stretches time itself. To an outside observer, matter falling toward the event horizon appears to slow, approaching but never quite crossing, fading into red-shifted invisibility. To the falling matter, the journey is brief and final. Two perspectives, both valid, both describing the same phenomenon from different vantage points. Phoenix A magnifies this effect to a degree that strains comprehension. Its event horizon would span more than 500 billion kilometers, roughly 100 times the distance from the Sun to Pluto. It is a shadow so vast that if placed at the center of our solar system, it would swallow every planet whole. And yet, even at that scale, it remains a mathematical boundary, not a surface. There is no solid edge, no wall of darkness, just a region where gravity becomes absolute. Space curves inward so steeply that all paths lead to the same destination. Inside that region, the known laws of physics break down. Our equations falter. Concepts like time and distance lose their meaning. Some theorists suggest that the core, or singularity, may not even exist as a true point of infinite density, but as something more complex, perhaps a ring of energy, or a bridge to another region of space-time. But these are ideas we cannot test, at least not yet. Phoenix A is too far away, and too hidden behind its own event horizon, to reveal such secrets directly. Still, humanity persists in trying. Across the planet, vast networks of radio telescopes are being linked together to form instruments capable of imaging the immediate environments around black holes. The Event Horizon Telescope, which captured the first image of the black hole in M87, works by combining signals from observatories thousands of kilometers apart. Though Phoenix A is more distant than M87, the same techniques can be used to study its emissions, its jets, and the ripples it sends through surrounding space. Each measurement adds another piece to the puzzle, narrowing the possibilities and helping us refine our understanding of these cosmic engines. It's remarkable to think that our species, confined to a small rocky planet orbiting a modest star, has developed the tools to probe such distant and powerful objects. The photons that tell us about Phoenix A began their journey before our planet's continents had settled into their current shapes. They crossed intergalactic space, passing through clusters, filaments, and cosmic voids, until they finally struck the sensors of a human-made machine. And from those faint signals, we infer the presence of something that weighs 100 billion suns. That is the quiet triumph of astronomy. Not that we conquer the universe, but that we learn to listen to it. As we move deeper into this story, we'll trace how such immense structures come to exist at all. What forces allow a black hole to grow so enormous? How does it feed? And what happens to the matter that ventures too close? These questions lead us into the heart of the Phoenix cluster itself, where galaxies drift through clouds of superheated plasma and light bends subtly under the influence of unseen gravity. Somewhere in that vast expanse, Phoenix A continues its patient work, shaping and being shaped by the cosmos around it. The night sky above you may look still, but every point of light is in motion, every cluster and nebula alive with the slow dance of creation and collapse. The same physics that governs Phoenix A also governs the atoms in your body. Gravity, magnetism, radiation, the same fundamental interactions play out across scales from subatomic to intergalactic. In understanding one, we understand a little of the other. Perhaps that's why stories like this feel so strangely comforting. They remind us that even in the face of such immensity, there is connection, order, and meaning. Phoenix A, for all its enormity, is not alien to us. It is made of the same universe that made us. Its gravity may hold galaxies, but its story holds our imagination. A black hole doesn't shine, at least not in the way a star does. It emits no light, no sparkle, no reflection. It is, by definition, a region of space where light itself is trapped, and yet, around these regions of absolute darkness, the universe often stages its brightest displays. Phoenix A is a perfect example. What makes it visible from billions of light years away isn't the black hole itself, but the chaos it stirs into motion, the gas it heats, the jets it throws, the way it bends the light of entire galaxies. It's a shadow that outshines the very systems it consumes, an object so powerful that the light of its destruction becomes its signature. When astronomers first pointed their instruments at the Phoenix cluster, what drew their attention wasn't darkness, but brilliance. In X-rays, the region glowed with astonishing intensity. The Chandra X-ray Observatory, captured images showing vast plumes of hot gas, the result of ancient explosions from the cluster's centre. This was no quiet corner of space. It was an arena of energy, a furnace where physics met its extremes. At the heart of all that violence sat Phoenix A, its presence invisible yet unmistakable. The surrounding radiation told its story, the temperature of the gas, the symmetry of the jets, the ripples spreading outward like sound through air. To understand why a black hole can outshine an entire galaxy, you have to imagine what happens to matter when gravity becomes absolute. Around Phoenix A, gas drawn from the cluster's core spirals inward, forming what's called an accretion disk. This disk isn't calm or orderly, it's turbulent, chaotic, driven by magnetic forces and friction. The gas compresses and heats as it falls, reaching temperatures of millions of degrees. At that point, it emits light across the spectrum, visible, ultraviolet, X-rays, radio waves, all produced by matter on the brink of annihilation. It's like a cosmic warning flare, an announcement that something nearby has crossed the threshold of no return. In visible light, you wouldn't see much. The cluster would look like a faint smudge of galaxies, their starlight stretched and dimmed by distance. But switch to the wavelengths that reveal heat and radiation, and the story changes completely. Phoenix A lights up the cluster like a beacon. Its outbursts carve holes in the surrounding gas, leaving behind cavities tens of thousands of light-years wide. Each cavity marks a previous episode of activity, when the black hole was feeding more vigorously, ejecting enormous quantities of energy in the form of jets that extended far beyond the host galaxy. Those jets don't just disappear. They leave trails, structures, and imprints that last for hundreds of millions of years. It's strange to think of emptiness having such an impact. But black holes don't simply sit in the universe as passive sinks. They are engines. The gravitational energy released by matter falling into them is one of the most efficient processes known. A single gram of matter consumed by a black hole can release more energy than thousands of tons of TNT. On the scale of Phoenix A, that means each feeding event can release more energy than all the stars in its cluster combined. It is through this energy, not its darkness, that the black hole becomes visible. It's a paradox of sorts. We only know the deepest darkness by the light it creates. Phoenix A's brilliance in radio and X-ray frequencies tells scientists how recently it has been active. The jets it produces stretch across hundreds of thousands of light-years, forming lobes of plasma that glow faintly as electrons spiral through magnetic fields. These structures fade with time, cooling and dispersing, but their size allows astronomers to estimate how long the activity lasted and how powerful it must have been. In the case of Phoenix A, the data point to eruptions of almost unimaginable magnitude. Some estimates suggest that each outburst released energy equivalent to hundreds of trillions of atomic bombs. The shock waves from those events ripple through the surrounding gas, reheating it, stirring turbulence, and shaping the evolution of the entire cluster. This is the scale at which Phoenix A operates, not as a single object, but as a central influence. It dictates the rhythm of star formation in the galaxies nearby. It sets the temperature of the gas that fills the cluster. It even affects how galaxies merge, because the outflows it generates can push matter outward, slowing the gravitational collapse of smaller systems. The black hole's shadow becomes a kind of pulse that echoes through space for millions of years after each eruption. The discovery of such immense influence began with patterns that didn't make sense. In most galaxy clusters, the hot gas in the core cools slowly over time, feeding a steady but limited rate of star formation. The Phoenix cluster, however, seemed to be doing something different. Its central galaxy was forming stars at a rate hundreds of times faster than expected, consuming the gas reservoir like a wildfire. Astronomers realized that something must have disrupted the usual feedback process that keeps clusters in balance. The likely culprit was Phoenix A itself. Either it had recently awakened from dormancy, or it had entered a rare phase of intense accretion. The result was a burst of radiation so powerful that it temporarily overcame the cooling mechanisms of the cluster. That discovery changed how scientists thought about the relationship between galaxies and their central black holes. It became clear that these enormous objects aren't just side effects of galaxy evolution, they're drivers of it. Every major galaxy seems to host one, and their masses tend to correlate with the properties of their hosts. The larger the black hole, the larger the galaxy's central bulge of stars. This relationship hints at a deep connection between growth and regulation. Phoenix A may be the most dramatic expression of that connection. A system where the usual checks and balances have momentarily tilted, allowing us to see what happens when a black hole's influence runs free. Imagine standing somewhere on the outskirts of that cluster. If you could see in the right wavelengths, the view would be haunting. A faint reddish glow from the hot gas would stretch across the sky, rippled by the remnants of old shock waves. The galaxies would appear like soft lanterns scattered through mist, their light bent and distorted by gravity. At the centre, invisible yet dominating everything, would be Phoenix A. You wouldn't see the black hole itself, but you'd see what it does. The glowing jets extending like ghostly arms, the cavities where matter has been swept away, the shimmering turbulence where energy meets vacuum. It would be a landscape of extremes, silence and fury, cold and heat, emptiness and power. The more we learn about black holes like this, the more they challenge the limits of our understanding. How does something grow so large without tearing apart the system around it? How can it remain stable for billions of years? These questions aren't just technical. They strike at the heart of how we model the universe. The equations that describe gravity, thermodynamics, and particle physics all converge here, at the edge of a phenomenon we can observe but never touch. Phoenix A becomes a kind of laboratory, a natural experiment running on cosmic timescales. Scientists use the data from Phoenix A to test models of black hole accretion, feedback, and growth. By comparing the energy of its jets to the rate of star formation in the surrounding galaxies, they can estimate how often the black hole cycles between active and dormant phases. These cycles determine how clusters evolve. When the black hole is active, it heats the gas and prevents it from collapsing into new stars. When it quiets down, the gas cools and star formation resumes. In Phoenix A, the balance seems to have tipped more dramatically than usual, suggesting a recent surge of activity that temporarily overwhelmed the cluster's equilibrium. This alternating pattern of destruction and creation defines the life of a galaxy cluster. It's a rhythm that spans hundreds of millions of years, invisible to human senses but recorded in light and heat. Each pulse of radiation, each cavity in the gas, is a record of a moment when the black hole asserted its presence. Over time, these moments accumulate into the structure we see now, a vast web of filaments and voids, energy and matter intertwined. Phoenix A isn't a single event, but a continuous influence, a shadow that keeps reshaping its surroundings long after each burst of light fades. If we could compress those cosmic timescales into something we could perceive, the cluster would appear to breathe. Gas would flow inward toward the centre, ignite into radiation as it neared the black hole, and then be expelled outward in waves. The galaxies would drift slowly, pulled by gravity yet nudged by those same outflows. The entire system would seem alive, pulsing to the rhythm of physics itself. In that sense, Phoenix A isn't just the largest black hole we know. It's a symbol of how dynamic the universe truly is, even in its quietest corners. From a scientific perspective, measuring such an enormous object requires combining multiple techniques. Astronomers estimate its mass by studying the motion of stars and gas in the central galaxy, by modelling the temperature and density of the surrounding plasma, and by analysing the scale of the cavities produced by its jets. Each approach yields slightly different numbers, but all converge on the same conclusion. Phoenix A is astonishingly massive. Its gravity extends across light years, influencing everything within its reach. The data suggest that if you placed our entire Milky Way within its sphere of influence, it would barely register as a detail in its environment. The name itself, Phoenix, feels fitting. In mythology, the phoenix is a creature that burns, dies, and rises again from its ashes. The cluster mirrors that pattern. Outbursts from the black hole heat the gas, halting star formation. Later, as the gas cools, new stars ignite, and the cycle begins again. It's a process of cosmic renewal, a rhythm of extinction and rebirth that repeats across epochs. Phoenix A sits at the heart of that cycle, both the destroyer and the enabler, its gravity turning chaos into order, and order back into chaos. Even now, the cluster continues to evolve. Astronomers detect faint radio echoes of past eruptions, and they model how the gas might behave in future cycles. Each observation adds detail to the story, but the outline remains the same, a vast system bound together by a single gravitational source. For every galaxy that orbits within the cluster, for every star forming in its outskirts, the unseen influence of Phoenix A is there, subtle yet absolute. It's easy to think of a black hole as something remote, something detached from human experience. But the physics at play there, the energy conversions, the interplay of gravity and motion, are the same principles that govern everything else. The difference is only in scale. What happens in the heart of the Phoenix cluster is a magnified version of the same forces that keep planets orbiting stars, that cause tides to rise and fall, that allow galaxies to form. When you look at it that way, Phoenix A isn't an outlier. It's an expression of universal law pushed to its furthest extreme. From Earth, we can only glimpse its effects. The photons that reach our telescopes have crossed unimaginable distances. By the time they arrive, their energy is stretched, their wavelengths redshifted by the expansion of space itself. What we see is a faint echo of a reality that once was, yet it's enough to tell us a great deal. It tells us that the universe is vast, that its mechanisms are both violent and delicate, and that even in darkness there is structure, purpose, and balance. The Phoenix cluster is not simply a collection of galaxies drifting through emptiness. It is a living system, enormous beyond imagination, where heat, gravity, and time weave together into something that almost feels like a pulse. The heartbeat of this cluster comes from the balance between cooling and heating, creation and destruction, expansion and collapse. It's a rhythm that unfolds over billions of years, but when viewed through the steady eyes of astronomy, it becomes something we can almost sense. The Phoenix cluster is where the largest black hole ever discovered, Phoenix A, resides. It is both the product of its surroundings and the force that keeps them in check. In the grand stillness of space, this cluster hums with energy that never quite fades. If we could somehow see it as it really is, without the limitations of our human eyes, it would look like a glowing web suspended in a dark ocean. Each galaxy would appear as a small island of light surrounded by an invisible sea of plasma. Between these galaxies lies a medium so hot that it shines in X-rays, with temperatures in the tens of millions of degrees. This gas doesn't form stars because it's too warm to collapse. Instead, it fills the space between galaxies like a vast ocean of energy, held in place by the combined gravity of the cluster. Every particle in that gas moves under the pull of the cluster's central mass, and in the very center of it all sits Phoenix A, shaping and being shaped by everything around it. From Earth, we observe this system as it was 6 billion years ago. The light that reaches our telescopes carries the story of a younger universe, one where the Phoenix cluster was still settling into its current form. In visible wavelengths, the galaxies appear as golden smudges, their stars ancient and red. But switch to the realm of X-rays, and the view changes completely. The cluster lights up with intensity, revealing the hot intra-cluster medium, the glowing plasma that acts as the lifeblood of the system. It is within this ocean of gas that Phoenix A releases its influence, generating waves of energy that ripple outward like sound through air. This balance between heating and cooling is the key to the cluster's heartbeat. Without the black hole's eruptions, the gas at the centre would cool and condense rapidly, forming stars at a rate too high to sustain. The cluster would burn through its supply of fuel and fade long before its time. But Phoenix A prevents that. When it feeds, it releases jets of energy that reheat the surrounding medium, slowing the formation of new stars and restoring equilibrium. Over time, this creates a feedback loop. Gas cools, the black hole awakens, energy surges outward, and the process resets. The result is a slow, steady rhythm of activity, a cosmic heartbeat that keeps the cluster alive. Astronomers have studied this rhythm by mapping the cluster in different wavelengths. The cavities carved in the X-ray gas mark the sites of previous outbursts, each one an echo of the black hole's past activity. These cavities can be tens of thousands of light years across, and their size tells us just how much energy was released. Each event injects enough power into the surrounding gas to offset the cooling for hundreds of millions of years. It's an elegant form of regulation, one that operates without intention or consciousness, driven purely by the laws of physics. Yet when you step back and consider it, the pattern feels almost biological. Heat builds, pressure releases, balance returns, a heartbeat slow and ancient, resonating through the fabric of space. At the core of the Phoenix cluster, the central galaxy dominates the scene. It's massive, far larger than the Milky Way, and rich with old stars. But unlike most galaxies and clusters, which tend to be quiet and stable, this one is active. Streams of gas fall toward its centre, feeding both star formation and the black hole. Observations from telescopes like the Atacama Large Millimeter Array have revealed filaments of cool gas stretching for tens of thousands of light years. These filaments act as the veins of the system, carrying material inward toward the black hole and outward toward regions where new stars are born. In this way, Phoenix A and its host galaxy form a closed system, a vast cycle of matter transforming under the influence of gravity and energy. For a time, scientists were puzzled by how active the Phoenix cluster seemed. The rate of star formation in its core was extraordinary, hundreds of solar masses per year. That's hundreds of times faster than what we see in typical cluster galaxies. Something had disrupted the normal feedback loop. Either the black hole had gone quiet, allowing the gas to cool unchecked, or it had erupted in such a way that its energy didn't reach the right regions to prevent condensation. Whatever the reason, the cluster had entered a rare phase of rapid growth, a heartbeat accelerating for a cosmic moment before returning to its steady rhythm. These fluctuations remind us that even the largest systems in the universe are not static. They evolve, shift, and adapt according to the delicate balance of forces within them. The Phoenix cluster is enormous, stretching over millions of light years, but is also fragile. Too much heating, and the gas disperses, halting star formation entirely. Too much cooling, and it collapses inward, fueling a surge of activity that could destabilize the core. Somehow, through countless cycles of energy release and decay, the system maintains its balance. The regularity of this process is what gives the cluster its sense of a heartbeat. A repeating pattern of cause and effect, a rhythm written in plasma and gravity. When scientists translate the data into visual models, they can see the cluster breathe. X-ray maps show bubbles expanding outward from the centre, their edges glowing faintly as they interact with the surrounding gas. Over time, these bubbles rise through the cluster like hot air balloons, mixing the plasma and distributing heat. As they fade, new ones form closer to the centre, marking the next pulse of activity. The intervals between these pulses are vast by human standards, tens or hundreds of millions of years, but within the lifespan of the universe they are as regular as a heartbeat. What's fascinating about the Phoenix cluster is how its immense scale magnifies simple processes that happen everywhere. Gravity pulls matter inward, pressure pushes it outward, and energy flows from hot to cold. The same principles that govern weather patterns on Earth govern the behaviour of the gas in this cluster, only on scales of light years instead of kilometres. The turbulence of the hot plasma, the cooling flows, the feedback from the central black hole, all follow the same physical laws that describe storms in our own atmosphere. The difference is time. Everything here happens so slowly that we only see snapshots of its evolution, frozen moments in a process that will continue long after our civilization has vanished. The Phoenix cluster also offers clues about how the largest structures in the universe come together. Galaxy clusters like this one are formed through mergers, smaller groups of galaxies colliding and combining under gravity's pull. Each merger brings new gas, new stars, and sometimes new black holes. These collisions create shock waves that ripple through the cluster, heating the gas and stirring turbulence. Over billions of years, the cluster settles into a kind of dynamic equilibrium, its components orbiting a common centre of mass. Phoenix A, being the largest black hole, anchors this structure. It sits at the gravitational centre, dictating the pace at which energy moves through the system. One of the most striking aspects of the Phoenix cluster is the sheer scale of its environment. The hot gas that fills it outweighs all the stars in its galaxies combined. This gas emits most of its energy in X-rays, which is why clusters are often first detected in that range. By studying the distribution of this radiation, astronomers can map the cluster's mass and structure. In Phoenix, the X-ray glow is so intense that it immediately drew attention. It revealed a core much denser and brighter than expected, suggesting a history of extreme heating and cooling. The patterns within that glow are like the vibrations of a drum, each wave a trace of energy released by the central black hole. When viewed as a whole, the Phoenix cluster embodies the interplay between extremes. Hot and cold, light and dark, chaos and order, they coexist in constant tension. It's easy to imagine that such vast forces would cancel each other out, leaving nothing but emptiness. But instead the result is structure. Galaxies orbit in stable paths, gas flows through predictable channels, and energy cycles between forms. The cluster's stability emerges not from stillness, but from motion. Every burst of radiation, every cooling filament, every gravitational tug contributes to a larger balance. It's this harmony of opposites that gives rise to the cluster's enduring vitality. Even from our distant perspective, we can measure the rhythm of that vitality. The temperatures, densities, and emissions of the gas follow patterns that correspond to the activity of the black hole. When Phoenix A releases energy, the gas heats and expands. When it quiets, the gas cools and condenses. This alternating pattern can be detected in the data, a measurable oscillation on cosmic scales. The regularity of this process provides insight into how black holes and galaxies co-evolve. It shows that feedback isn't random, it's part of a natural cycle that sustains the structures of the universe. It's worth pausing to consider just how immense these processes are. The smallest ripple in the cluster's gas might span hundreds of thousands of light years. A single wave of heating could take millions of years to move from the centre to the outskirts. And yet, from our perspective, these are instantaneous compared to the lifetime of the universe. The heartbeat of the Phoenix cluster is slow, but it never stops. Each pulse echoes through space for eons, maintaining a balance that allows stars to form, galaxies to persist, and the cluster itself to endure. If we could listen to the Phoenix cluster, it wouldn't sound like anything we know. The vibrations in its gas are far too low for our ears, with frequencies measured in cycles per hundreds of millions of years. But scientists can translate those waves into sound by compressing the timescale. When they do, the cluster produces deep, resonant tones, an eerie reminder that even in silence the universe has its own kind of music. The Phoenix cluster's song would be a slow, continuous hum, punctuated by bursts of intensity when the black hole stirs. It's the sound of energy transforming, of gravity and radiation finding equilibrium, of a system larger than comprehension, yet operating with the precision of a heartbeat. In studying this cluster, astronomers aren't just measuring numbers or analysing spectra. They are listening to the rhythm of the cosmos itself. They are tracing the pathways by which matter becomes light, and light becomes structure. They are observing how the universe keeps time not with clocks, but with cycles of energy and motion. The Phoenix cluster is one of the clearest examples we have of these principles in action. Its scale magnifies the patterns that exist everywhere, from the smallest galaxies to the largest cosmic webs. It shows us that even in apparent chaos there is order. Even in stillness there is movement. As the cluster continues its slow oscillation, the story of Phoenix A unfolds alongside it. The black hole is both the cause and the consequence of the cluster's behaviour. Its gravity anchors the system, its energy sustains it, and its hunger defines the boundaries of what can exist within it. The heartbeat of the Phoenix cluster, steady and vast, is not just the sound of gas cooling and heating, it's the sound of the universe regulating itself. Every cycle, every ripple, every pulse is a reminder that even the darkest corners of space are full of motion, balance and continuity. And somewhere within that grand rhythm, Phoenix A waits for its next breath, its next surge of energy, its next pulse of light that will echo through the cluster and across the cosmos. Black holes are often described as the universe's ultimate consumers, but the word hunger feels more fitting than consumption. They don't simply take, they persist. They wait, pull, and devour across billions of years, never full, never finished. Phoenix A embodies this kind of endless appetite. It sits at the centre of the Phoenix cluster like a gravitational heart that never stops drawing matter toward it. Its feeding habits are not quick or chaotic in a cinematic way. They are patient, methodical, and constant. It feeds on the gas that drifts through its host galaxy, on the dust torn from nearby stars, and occasionally on entire fragments of galaxies that wander too close. It eats slowly, invisibly, through mechanisms so extreme that human intuition barely stretches far enough to contain them. The appetite of a black hole begins with gravity. At small scales, gravity keeps planets circling stars and moons circling planets. But near a black hole, gravity becomes absolute. It stretches and compresses space itself, creating a region where escape is impossible once you cross a boundary called the event horizon. Nothing that passes through that horizon can return. Not light, not energy, not information. From the outside, this boundary looks like emptiness, but in reality it marks the point at which space-time itself collapses inward. For Phoenix A, the event horizon is staggeringly vast. Its diameter would be measured not in kilometres, but in hundreds of billions of them. A sphere that large would swallow our entire solar system many times over. Yet even this scale fails to convey what is truly happening there. The event horizon is not a surface. It is the edge of knowability, the place where physics as we understand it ceases to function. The feeding process begins long before matter ever reaches that point. Gas drawn toward Phoenix A doesn't fall directly inward. It spirals, forming a rotating disk known as an accretion disk. Within that disk, particles rub and collide at near-relativistic speeds. Friction turns their motion into heat, and heat into light. This process can produce temperatures so high that the gas glows across the electromagnetic spectrum, from radio waves to X-rays. It's a strange irony. The closer matter gets to disappearing into darkness, the brighter it becomes. Phoenix A's accretion disk would outshine entire galaxies if we could see it up close. The light we observe from billions of light years away is only a whisper of that intensity, filtered through space and time. Around the disk, magnetic fields twist and tighten. These fields can launch jets of plasma outward at nearly the speed of light, perpendicular to the plane of the disk. The jets are a byproduct of the feeding process, a kind of venting of excess energy. They don't carry matter from inside the black hole, but from just outside the event horizon. particles that were close enough to be accelerated by the magnetic fields, but lucky enough to escape before falling all the way in. These jets are one of the main reasons we know Phoenix A exists. They stretch for hundreds of thousands of light years, visible to our telescopes as faint radio structures. Each jet is a monument to the black hole's hunger, an expression of its feeding translated into energy. Black holes like Phoenix A grow in spurts. They spend most of their existence in relative quiet, pulling in small amounts of gas from their surroundings. Then, every so often, conditions align to trigger a feeding frenzy. A merger between galaxies, a stream of cooling gas, or a collision within the cluster can deliver new material to the center. The black hole awakens, its accretion disk brightens, and its jets flare with renewed intensity. For millions of years it gorges, releasing more energy than all the stars in its cluster combined. When the supply dwindles, it settles again, leaving behind the remnants of its outbursts in the form of bubbles and shock waves. This pattern of feast and rest has likely repeated for billions of years, each cycle carving its history into the gas of the cluster. To understand just how much Phoenix A can consume, imagine a cloud of gas 1,000 light-years across drifting toward the cluster's center. Gravity pulls it inward, stretching it into filaments as it approaches. Within those filaments, some gas collapses to form new stars, but much of it continues its descent toward the black hole. By the time it nears the accretion disk, the gas is moving at a significant fraction of the speed of light. The potential energy it carries is immense. As it spirals inward, magnetic turbulence converts that potential energy into heat and radiation. Only a small fraction of the gas actually crosses the event horizon. The rest is blasted away in winds or jets, carrying off the energy of the accretion process. This combination of inflow and outflow defines the feeding pattern of Phoenix A, voracious yet self-limiting, a hunger that fuels its own restraint. The scale of this feeding is difficult to visualize. If Phoenix A were consuming matter at its theoretical maximum rate, the so-called Eddington limit, it could devour several solar masses worth of material every year. Over the lifetime of the universe, that rate would allow it to reach its current mass of around 100 billion suns. Whether it actually feeds that efficiently all the time is uncertain, but even at lower rates, the accumulated growth over billions of years is staggering. Each new wave of accretion adds to its mass, and the more massive it becomes, the stronger its pull. Hunger feeds hunger. The mechanisms that deliver matter to the center of the cluster are themselves complex. The galaxies within the Phoenix cluster are constantly interacting, their orbits distorted by gravity, their outer regions stripped by tidal forces. Streams of gas flow between them, converging toward the gravitational center like rivers toward a basin. Some of this gas cools enough to condense into filaments that stretch across intergalactic space. These filaments act as conduits, feeding the central galaxy and, ultimately, Phoenix A. It's a system of cosmic plumbing on scales far beyond human experience, with flows that take millions of years to complete. Yet even at that pace, the result is constant. Material finds its way to the center, and the black hole grows. One of the most striking discoveries about Phoenix A is the evidence of multiple generations of outbursts recorded in the surrounding gas. The cavities seen in X-ray images are relics of past eruptions. Each cavity corresponds to a period when the black hole was actively feeding and releasing energy through jets. By measuring the size and distance of these cavities, astronomers can estimate how long ago each outburst occurred. The results reveal a timeline spanning hundreds of millions of years, a record of activity as regular as the beats of a heart. Each beat represents a surge of hunger, a time when the black hole consumed enough to alter the state of the entire cluster. This persistent cycle raises fundamental questions about how black holes stop growing. In theory, there should be a natural limit. As the black hole feeds, the radiation from its accretion disk exerts pressure on the incoming gas. Eventually, that radiation becomes strong enough to push matter away, cutting off the supply. For most black holes, this balance keeps their growth in check, but for Phoenix A, the balance must have tipped repeatedly in favour of accretion. Its environment provided a steady reservoir of gas, and its gravity ensured that enough of it kept falling inward despite the outward pressure of radiation. The result is a black hole that has reached near the upper limits of what we believe possible. At these extremes, even time behaves differently. Close to the event horizon, gravity slows the flow of time relative to the rest of the universe. For a distant observer, matter approaching the horizon appears to slow, fade, and freeze just above it. To the infalling matter, the crossing happens quickly and irrevocably. Both perspectives are true. The black hole's hunger unfolds on timescales that differ depending on where you stand. For the cluster, each feeding event lasts millions of years. For the matter falling in, it ends in moments. It's a reminder that even the act of consumption is relative, stretched by the fabric of space-time itself. As Phoenix A continues to grow, it affects everything around it. The energy released during accretion heats the gas in the cluster, preventing it from cooling too fast. This feedback regulates star formation, determining how many new stars are born and where they appear. In this way, the black hole's hunger shapes the visible universe. Every galaxy, every cluster, owes part of its structure to the invisible appetite at its centre. Phoenix A is not an anomaly, but an exaggeration, a magnified version of a process that occurs everywhere. Its endless feeding is simply the universe expressing its fundamental tendency toward transformation. There's a certain paradox in this idea. The more Phoenix A consumes, the more it gives back in energy. The heat and light produced by its accretion radiate outward, enriching the space around it. The same hunger that swallows matter also sustains the cluster's balance. Without it, the gas would cool too quickly, collapsing into stars until nothing remained to form future generations. The black hole's appetite, destructive as it seems, is part of what keeps the system alive. It's a cycle of nourishment written on cosmic scales: devour, release, stabilize, repeat. If we could observe Phoenix A over the full span of its existence, we would see this cycle repeating like a natural law. Streams of gas flowing inward, bursts of energy flowing outward, the cluster responding and adjusting each time. It would be easy to mistake this for intention, to imagine the black hole as a creature choosing when to eat and when to rest. But it is simpler and more profound than that. It is the physics of gravity and motion, energy and equilibrium, hunger without thought, purpose without design. Even in its quiet phases, Phoenix A is never truly still. Gravity ensures that the flow of matter continues, however slowly. Each particle that drifts near the event horizon becomes part of a process that has been running since the dawn of the universe. Somewhere deep inside, beyond the reach of observation, all of that matter compresses into forms we can't describe. Whether it becomes a singularity or something more complex, no one knows. What we do know is that nothing escapes. Every atom that crosses the horizon becomes part of the black hole's mass, adding to the total, deepening its gravity, and ensuring that its hunger continues. If the universe endures long enough, even the stars will eventually die. Galaxies will fade, leaving behind remnants, white dwarfs, neutron stars, and black holes. Over trillions of years, those remnants will drift together and merge, forming ever larger black holes. In that distant future, hunger may be the only activity left. Black holes like Phoenix A will continue to consume what remains until there is nothing left to eat. And then, perhaps, they too will fade, evaporating slowly through the faint emission predicted by quantum theory. But that end is so far away it barely matters to us. For now, Phoenix A feeds, and the universe around it continues to respond. The hunger of a black hole is not evil or violent in any human sense. It's simply the continuation of gravity's logic. Matter moves where it must, energy flows as it can, and balance is maintained through processes that seem endless because they are measured on scales beyond our comprehension. Phoenix A's appetite connects the smallest particles of gas with the largest structures in the cosmos. It is a reminder that nothing in the universe is truly separate. Everything falls towards something. Everything contributes to something else. Somewhere, in the core of the Phoenix cluster, that hunger persists. Gas still spirals inward, jets still flare outward, and space itself still bends under the weight of all that mass. The process has no beginning we can pinpoint and no end we can foresee. It simply is, a perpetual conversion of matter into energy, of potential into history. The cluster's galaxies orbit quietly, the hot gas glows, and at the centre, Phoenix A waits, patient and endless, a hunger that never ends. Measuring something that cannot be seen might sound like an unsolvable puzzle, yet that is precisely what astronomers do when they study black holes. There is no surface to reflect light, no visible shape to outline, no direct signal that says, here is the edge, here is the core, here is its size. What they have instead are effects, the influence a black hole exerts on everything around it. For Phoenix A, that influence is so immense that it extends across millions of light years, bending not only the paths of stars and gas, but the very fabric of space itself. To weigh the unseeable, scientists must read those distortions, measure those motions, and interpret the faint radiation that escapes from the edge of oblivion. In doing so, they have pieced together a story of a black hole so massive that its gravity governs an entire cluster of galaxies. The first step in weighing any black hole is to look for movement. Gravity leaves a signature wherever it acts. In the Milky Way, astronomers estimate the mass of our central black hole, Sagittarius A, by watching nearby stars orbit around an apparently empty point. The faster they move, the stronger the gravitational pull they are responding to, and from that motion, mass can be inferred. The same logic applies to Phoenix A, though the scale is vastly larger. No single star orbits close enough to trace its path, so scientists look instead at the motions of gas and at the shape of the surrounding radiation. The speeds involved are staggering. Gas near the centre of Phoenix A whirls around at thousands of kilometers per second, creating pressure and temperature patterns that reveal the mass pulling on it. Observations in multiple wavelengths are crucial because no single kind of light tells the whole story. Invisible light, the central galaxy of the Phoenix cluster, is a brilliant yet relatively featureless oval, dominated by ancient stars. But when astronomers switch to X-rays, they see the hot gas that fills the cluster's core. The way this gas moves, the way its brightness changes with distance from the centre, provides clues to the gravitational potential shaping it. If the gas were moving only under the combined gravity of the cluster's galaxies and dark matter, its distribution would follow predictable patterns. Instead, there is an extra pull, an unseen force at the very centre, deep enough to require something extraordinary, a black hole tens of billions of times more massive than the Sun. This method of mass estimation is known as hydrostatic equilibrium modelling. The idea is simple, though the execution is not. The gas in the cluster is in a kind of balance between the inward pull of gravity and the outward push of its own heat and pressure. By measuring the temperature and density of that gas, astronomers can determine how strong gravity must be to hold it in place. The deeper the gravitational well, the more massive the object at its centre must be. Using data from the Chandra X-ray Observatory and other instruments, researchers can map that balance across the cluster. For Phoenix A, the results point to a black hole of nearly 100 billion solar masses, a figure that pushes the limits of what theory predicts. But X-rays tell only part of the story. Radio observations add another layer. When the black hole's jets carve cavities into the surrounding gas, they create voids that can be seen in both X-ray and radio images. The size and energy of these cavities reveal how powerful the outbursts were. The bigger the cavity, the more energy was required to form it, and that energy in turn depends on the black hole's mass. By comparing the observed cavities with simulations of jet activity, scientists can estimate how massive a black hole must be to produce such effects. In Phoenix A, the cavities are vast. Each one could hold multiple Milky Way galaxies. The energy required to inflate them matches what would be expected from a black hole at least tens of billions of solar masses in size, confirming what other methods suggest. Another indirect approach involves studying the brightness of the cluster's central region. When gas falls toward the black hole, it releases radiation. The maximum luminosity a black hole can sustain before radiation pressure pushes material away is known as the Eddington limit. By measuring how bright the core appears and comparing that to the Eddington limit, astronomers can estimate how efficiently the black hole is feeding, and, from that, infer its mass. If Phoenix A's luminosity represents only a small fraction of its Eddington limit, then its mass must be enormous to allow such a high output without blowing away the surrounding gas. The numbers align again with a mass in the range of 100 billion suns. Even with these multiple lines of evidence, uncertainty remains. The problem with black holes is that every measurement depends on assumptions about what lies just beyond observation. Is the gas perfectly in equilibrium? Are the jets symmetrical? How much of the observed energy comes directly from accretion versus from other processes in the cluster? Each question adds a margin of error, and when dealing with scales this large, those margins can span billions of solar masses. Still, the consensus that emerges is remarkably consistent. Phoenix A is one of the most massive black holes ever discovered, perhaps the most massive of all. To appreciate what that number means, it helps to compare. The black hole at the centre of our Milky Way has about 4 million times the mass of the Sun. The one at the centre of the giant galaxy M87, which was famously imaged by the Event Horizon telescope, has about 6.5 billion solar masses. Phoenix A dwarfs them both. If you could somehow place Sagittarius A and M87's black hole side by side with Phoenix A, the smaller ones would barely register. Its gravitational radius is so vast that the orbit of Pluto would fit easily within it, with room to spare for several more solar systems. But how can we be sure we're not overestimating? Astronomers cross-check their results by comparing Phoenix A to other clusters with similar properties. The relationship between a galaxy's mass and the mass of its central black hole, known as the M-sigma relation, provides one benchmark. Galaxies with higher stellar velocity dispersions, that is, faster-moving stars, tend to host more massive black holes. For Phoenix A's central galaxy, the stellar motions are extreme, consistent with the pull of something extraordinarily heavy. When the numbers are plugged into the established correlations, they again point toward a black hole near the 100 billion mark. The evidence converges from multiple directions, each independent, each telling the same story. There's a quiet elegance in this indirect way of knowing. To weigh something invisible requires not brute force but inference, patience, and careful measurement. Every photon of light, every radio wave, every X-ray counts as a clue. Astronomers build models, test them against observations, adjust parameters, and watch how the simulated gas behaves. When the model matches reality, they know they're close. It's like listening to a faint rhythm through layers of noise until the pattern becomes clear. The mass of Phoenix A is that pattern, the result of countless observations converging on a single conclusion about something that will never be seen directly. What's remarkable is how consistent the universe is in rewarding such careful deduction. When the first estimates of Phoenix A's mass were published, they seemed almost too large to believe. Some researchers suspected that the methods might have overestimated, that the assumptions about equilibrium might not hold. But as new data arrived from different observatories, XMM, Newton, Chandra, the Atacama Large Millimeter Array, the results stayed steady. The same range of numbers appeared again and again. It became clear that Phoenix A was indeed an outlier, not because of an error, but because the universe occasionally produces extremes beyond what we expect. Even so, the act of measuring a black hole remains one of the most humbling exercises in science. We weigh it not by touching or seeing, but by listening to its surroundings. We watch how galaxies orbit, how gas flows, how radiation flickers, and from those signs we infer the existence of something that bends space so completely that even light cannot leave. In the case of Phoenix A, this process takes on a kind of poetic symmetry. The largest known black hole reveals itself through the faintest traces, ripples in hot gas, echoes of ancient explosions, light filtered through distance and time. It is the universe's way of whispering its secrets, just loud enough for those who are patient enough to hear. The precision of these measurements has improved dramatically in recent decades. Instruments like the James Webb Space Telescope and ground-based interferometers allow astronomers to study clusters with unprecedented resolution. As data accumulates, the models grow more refined. One day, it might even be possible to observe the immediate environment around Phoenix A directly, detecting the subtle flicker of light from its accretion disk or the structure of its jets. For now, what we have are mosaics of information pieced together across wavelengths and years. The result is a coherent picture built entirely from evidence that never points to the black hole itself, but always to what it does. That distinction matters. When scientists say they have weighed Phoenix A, they are not claiming to have seen its outline. They are saying that the universe behaves as though such a mass exists, that gravity, motion, and radiation all respond to something immense and central. It is the same logic used to infer the presence of planets around distant stars. You see the wobble, you feel the pull, and you know something unseen must be there. In astronomy, absence can be as revealing as presence. This way of knowing reflects a deeper truth about our relationship with the cosmos. Much of what we understand comes not from direct contact, but from interpretation. The universe rarely offers clear, unambiguous signs. It hides its workings behind distance, time, and scale. Yet from those faint signals, we reconstruct entire histories of stars, galaxies, and black holes like Phoenix A. To weigh the unseeable is to engage with that mystery, to accept that knowledge often comes through its shadows. As measurements continue, Phoenix A remains a benchmark, a reference point for the study of extreme cosmic objects. Its mass challenges current theories of how black holes form and grow. To reach 100 billion solar masses, it must have accumulated matter with extraordinary efficiency over billions of years. Some scientists propose that it began as a direct collapse black hole, formed from massive gas clouds in the early universe rather than from the death of a single star. Others suggest repeated mergers with other black holes built it up step by step. Each hypothesis depends on what we learn from its mass, because that number tells us not just how big it is now, but how long and how fast it must have been feeding. The more precisely we weigh Phoenix A, the more we learn about cosmic evolution itself. Its existence shows that the universe was capable of producing colossal structures early on, that gravity had already begun organizing matter into clusters and galaxies within a few billion years of the Big Bang. Every refinement of its measurement adds another piece to the puzzle of how the cosmos went from a sea of hydrogen and helium to the structured universe we see today. And so, the process continues. New instruments come online, new observations are made, new models are tested. Each refinement brings us closer to understanding the true scale of Phoenix A. But even when we know its mass to the last decimal, it will remain unseen. Its boundary will stay invisible, its interior unknowable. What we have instead is the pattern of its influence, the record of its weight written in the motion of galaxies and the glow of gas. The act of weighing something like Phoenix A is both scientific and philosophical. It forces us to confront the limits of perception and the power of inference. It reminds us that the most significant forces in the universe often hide behind silence. And in that silence, there is a kind of beauty, a quiet agreement between evidence and imagination. We may never see Phoenix A directly, but by observing its surroundings, we have brought its immense presence into human understanding. As the measurements grow more precise, the image becomes clearer, a cluster humming with energy, gas swirling under invisible influence, galaxies orbiting a mass that outweighs them all. The black hole remains unseen, but its weight shapes everything around it. That, in the end, is how we know it is there. Phoenix A, the unseeable giant, the anchor of the Phoenix cluster, measured not by light but by gravity, revealed through motion, defined by absence, a shadow so heavy that it bends the universe itself. Jets from a black hole are not what most people imagine when they hear the word jet. There is no sound, no explosion, no colour in the ordinary sense. They are streams of particles, invisible to human eyes, moving at nearly the speed of light, extending for hundreds of thousands of light years. Phoenix A produces jets so immense that they shape the entire structure of its host galaxy, and even the surrounding cluster. In photographs taken in radio wavelengths, these jets appear as faint arcs or lobes stretching outward from the centre, carving holes in the hot gas that fills the cluster. In X-rays, the cavities they leave behind are darker regions amid the glowing plasma, evidence of energy released on scales that dwarf anything else in the known universe. It is through these quiet eruptions that Phoenix A announces itself. They are the expression of fury translated into silence, of violence slowed into the calm language of astrophysics. To understand how such jets form, it helps to picture the region just outside the event horizon. There, matter falling toward the black hole does not drop straight in. It orbits, forming an accretion disk. The friction within that disk heats the gas to millions of degrees, causing it to emit intense radiation. At the same time, magnetic fields twist through the disk and funnel some of the charged particles along the black hole's poles. Those particles are accelerated outward, creating the twin jets that pierce the surrounding space. The process is both orderly and chaotic. Magnetic lines of force snapping and reconnecting, plasma compressed and ejected, energy transformed from rotational motion into radiation and momentum. The details are still the subject of research, but the result is clear. From a region smaller than our solar system, Phoenix A launches outflows that reach across hundreds of thousands of light years. When those jets encounter the hot gas of the cluster, they transfer their energy into it. The result is a pair of giant cavities where the gas has been pushed aside, like bubbles in boiling water. Each cavity can span tens of thousands of light years, and the energy required to create them is almost unimaginable. Scientists estimate that a single outburst from Phoenix A releases as much energy as all the stars in the Milky Way emit over hundreds of millions of years. Yet despite that violence, the process unfolds slowly. The jets inflate the cavities over tens of millions of years, and as the energy dissipates, the gas gradually returns to equilibrium. What looks like an explosion in a still image is, in truth, a controlled breathing of the cluster, an exhalation followed by calm. This balance between eruption and calm is one of the most remarkable aspects of black hole physics. The jets do not destroy the cluster, they stabilize it. Without them, the gas in the core would cool too quickly, collapsing and forming stars at an unsustainable rate. The outbursts from Phoenix A reheat the gas, preventing runaway cooling and keeping the cluster in a state of long-term balance. This self-regulating behavior, known as feedback, is one of the key mechanisms that shape galaxy evolution. In effect, the black hole acts as both destroyer and caretaker. It stirs the environment, releases heat, and then rests until the gas cools enough to fall inward again. The quiet fury of its jets is what allows the cluster to persist. In X-ray images, the marks of this fury are unmistakable. Chandra's instruments detect the cavities as symmetrical depressions in the glowing plasma, surrounded by bright rims where the displaced gas has been compressed. Further out, The faint ripples of older outbursts can still be seen, evidence of cycles repeating over billions of years. In radio wavelengths, those same cavities appear filled with the emission of relativistic electrons, tracing the paths of the jets long after the initial outburst has ended. The combination of these observations reveals a history written in light and absence. Each cavity, each ripple, a line in the record of Phoenix A's activity. The jets themselves are composed of particles moving so fast that time slows for them relative to the cluster around them. Their speeds are measured as fractions of the speed of light, 0.99 c, 0.99 c, numbers that compress vast energies into motion. Within those jets, the magnetic fields confine the plasma, preventing it from dispersing. Over time, the jets expand and cool, depositing their energy into the intracluster medium. The regions they create remain buoyant for hundreds of millions of years, before slowly rising and mixing with the surrounding gas. In that way, the outbursts of Phoenix A leave lasting imprints on the structure and temperature of the entire cluster. The scale of these events challenges ordinary comprehension. Each jet extends far beyond the boundaries of the central galaxy. If one could see them with the naked eye, they would appear as ghostly beams stretching across space, wider than the distance between galaxies. The light from those jets, shifted into radio frequencies by their speed, and the expansion of the universe reaches Earth after travelling 6 billion years. What we observe today is not what Phoenix A is doing now, but what it did when life on our planet was just beginning to take its first complex forms. The jets we see are ancient, fossilized evidence of a process that continues unseen in the present. Astronomers use these structures to estimate how much power the black hole releases during each active phase. By measuring the pressure and volume of the cavities, they can calculate the total energy required to create them. The results are staggering. Each outburst appears to release around 10 to plus 61 ergs of energy, a number so large it loses meaning outside scientific notation. For comparison, a typical supernova releases about 1051 ergs. That means a single episode from Phoenix A can equal the energy of 10 billion supernovae. And yet, unlike a supernova, which explodes in seconds, this energy is delivered gently, over vast periods, diffused through space until it becomes part of the cluster's quiet glow. It is this gentleness, this absence of abruptness, that makes the phenomenon so paradoxical. The jets of Phoenix A are furious in scale, but tranquil in their effect. They heat without destroying, sculpt without shattering. The cluster absorbs their energy the way an ocean absorbs the push of a slow tide. This contrast between violence and calm is central to understanding how the universe maintains order. Every apparent act of destruction carries within it the seed of stability. The fire that blazes from the black hole's poles keeps the surrounding galaxies intact. On smaller scales, the jets influence star formation directly. As they pass through the surrounding gas, they compress some regions while dispersing others. The compressed pockets can trigger the birth of new stars, while the dispersed regions prevent overproduction. In this way, Phoenix A's outbursts not only regulate the cluster's overall temperature, but also determine where and when stars appear. Observations from optical telescopes show filaments of young blue stars trailing along the paths of the jets, a subtle sign that even the most energetic forces can create beauty in their wake. The presence of these filaments suggests that the interplay between heating and cooling in the Phoenix cluster is particularly dynamic. The gas cools, falls inward, and triggers star formation, which then provides new material for the black hole to consume. The subsequent outburst halts the process temporarily, only for it to begin again later. This cyclical interaction keeps the cluster active, preventing it from becoming either too stagnant or too chaotic. The jets and the gas dance in a feedback loop that defines the cluster's long-term evolution. Understanding these processes requires not just observation, but simulation. Astrophysicists model the behavior of the jets using supercomputers, reproducing the conditions of plasma under extreme gravity and magnetism. These simulations show how jets carve paths through gas, how they entrain material, and how their energy dissipates. When the models are compared with the real data from Phoenix A, the match is striking. The shapes of the cavities, the distribution of temperature, the ripples in the X-ray glow, all align with the predictions. It is a rare case where the mathematics of theory and the images from observation speak the same language. Still, there are mysteries. We know that the black hole's spin plays a crucial role in launching the jets, but measuring that spin is extremely difficult. If Phoenix A rotates rapidly, as most models suggest, its spin could be storing enormous amounts of energy, waiting to be tapped by magnetic fields. That rotational energy may help power the jets, allowing them to continue for millions of years without exhausting the supply of infalling gas. Determining the exact contribution of spin versus accretion remains one of the open questions in astrophysics, and Phoenix A offers one of the best laboratories for studying it. There is also the question of symmetry. In many systems, one jet appears slightly brighter or longer than the other. This asymmetry can arise from differences in the surrounding medium or from relativistic effects, depending on the angle of observation. In Phoenix A, the jets are remarkably balanced, extending in opposite directions with similar power. This symmetry hints that the environment around the black hole is relatively uniform, at least on large scales. It suggests a stability that may explain how the cluster has remained coherent over billions of years, despite the enormous energies involved. When you think about these processes, it becomes clear that the phrase "quiet fury" is not poetic exaggeration but a literal description. The energy is real, the violence is immense, but the pace and distance make it appear calm. Everything happens so slowly that even explosions become gentle. In a human lifetime, nothing would change. The jets would remain steady. The cavities would drift imperceptibly outward. Yet across cosmic timescales, their influence is decisive. The Phoenix cluster's structure, temperature, and star formation history are all products of these gradual eruptions. Looking at images of Phoenix A's outflows, you see patterns that resemble organic forms, plumes, tendrils, arcs. It is easy to forget that each one represents distances measured in tens of thousands of light years. The apparent delicacy of the structures hides their strength. They are filaments of plasma held together by magnetic fields far more powerful than anything produced on Earth. The electrons within them spiral at nearly light speed, emitting synchrotron radiation that we detect as radio waves. That faint radio glow is all that remains of energy released long ago, a fossil light that tells us about processes that ended millions of years before our species existed. The quiet fury of Phoenix A's jets reminds us that energy in the universe rarely disappears. It changes form, moves from one place to another, fades slowly but never truly vanishes. The heat from those ancient outbursts still warms the gas of the cluster today. The ripples they created still travel through space, altering the pressure and density of the medium. The black hole's actions are recorded not in sound or light we can see directly, but in the shape and temperature of the cosmos itself. From the perspective of the cluster, these cycles are ordinary. They are part of its long rhythm, another expression of the balance that defines large-scale structure. For us, observing from billions of light years away, they are a window into the persistence of natural law. Gravity, magnetism, and motion act the same everywhere, producing order out of apparent chaos. Phoenix A's jets are simply one of the most dramatic demonstrations of that order. In the end, the fury subsides, the jets cool, and the cavities drift upward like bubbles through water. The cluster settles into temporary calm, but calm never lasts. As the gas cools and begins to fall inward again, the process will repeat. Phoenix A will awaken once more, the accretion disk will brighten, and new jets will form, reigniting the quiet fury that keeps the cluster alive. And so the cycle continues, slow and steady, a rhythm of fire and silence, the breath of a giant written across the stars. Darkness in the universe is not the absence of creation. It is one of its most efficient tools. The paradox is that black holes, the darkest entities we know, are among the most influential in shaping the luminous structures that fill the sky. Without them, galaxies would form differently, clusters would lack balance, and much of the universe would look unlike what we see. Phoenix A is perhaps the purest example of that paradox. It does not emit light of its own, but its presence determines where light can exist. It carves structure into chaos, imposes order on gas, and sets the pace at which stars are born. The darkness around it is not empty. It is sculpted, organized, and alive with gravitational intent. When scientists model galaxy formation, they quickly find that gravity alone cannot explain what they observe. If all the gas in a galaxy cluster were left to cool without interference, it would collapse rapidly, forming stars at rates far higher than we see. Over time, this unchecked star formation would exhaust the gas, leaving behind a dense collection of old stars and little else. Yet real clusters don't behave that way. Their cores remain rich with hot gas, and their star formation rates are moderate and self-regulating. The missing ingredient in the models turns out to be feedback, the influence of energy injected into the system by active black holes. In other words, darkness shapes creation by preventing it from running wild. In the Phoenix cluster, this principle operates on an extreme scale. The gas that fills the cluster's core is constantly cooling, losing energy by radiating in X-rays. If left alone, it would condense into new stars at a rate of thousands of solar masses per year. That would make the central galaxy a short-lived furnace of light. But Phoenix A interrupts that process. Each time it feeds, it releases jets of energy that reheat the gas, slowing or halting its collapse. The result is a long-term balance. Stars still form, but gradually in measured bursts rather than uncontrollable floods. The darkness at the cluster's center dictates the tempo of creation, ensuring that it continues not in a single flash, but across billions of years. To visualize this, imagine the cluster as an immense sphere of hot gas, with cooler filaments beginning to form near the core. Those filaments drift inward, pulled by gravity. As they approach the center, they are caught by the black hole's influence. Some of the gas falls into the accretion disk, igniting the next cycle of jet activity. When the jets erupt, they push outward, creating cavities in the gas and heating it once again. The filaments disperse, the cooling slows, and the process resets. This oscillation between cooling and heating defines the evolution of the cluster. Creation proceeds because destruction holds it back. Astronomers can see the fingerprints of this balance in the data. Optical images reveal tendrils of newly formed stars tracing the paths of the cooled filaments, while X-ray maps show the surrounding gas glowing at tens of millions of degrees. The filaments represent moments of surrender, when gravity overcomes pressure and allows matter to condense. The hot gas around them represents resistance, the black hole's response. In between lies equilibrium, a place where darkness and light meet and sustain each other. The Phoenix cluster is not a static scene. It's a negotiation between extremes, conducted in the language of temperature, density, and time. In the absence of this kind of regulation, galaxies would look very different. Without feedback from black holes, clusters would evolve too quickly, their gas consumed before it could participate in future cycles of formation. The universe would become dominated by old, cold systems, and the diversity of galaxies we see today would not exist. Black holes, by injecting energy back into their environments, slow the process down, stretching creation across eons. This prolonged timescale allows complex structures to emerge: spiral arms, galactic halos, networks of filaments linking clusters together. Darkness, through gravity and feedback, gives light the time and space to organize itself. There is also a subtler form of creation at work near black holes. The extreme conditions around their event horizons accelerate particles to enormous energies, producing radiation and magnetic fields that can extend across entire galaxies. These high-energy environments are laboratories of physics, generating cosmic rays and influencing the chemical evolution of the interstellar medium. In Phoenix A, the jets and outflows likely spread heavy elements, carbon, oxygen, iron, throughout the cluster, enriching the gas from which new stars and planets will eventually form. The act of feeding becomes an act of seeding, scattering the ingredients of future systems far beyond the black hole's immediate reach. This process connects directly to the broader history of the universe. In the early cosmos, when the first black holes formed from collapsing stars or from direct collapse of gas clouds, their outflows helped shape the growth of the first galaxies. They prevented runaway cooling, kept the early gas hot enough to delay star formation, and influenced how matter clustered under gravity. The same feedback mechanisms that operate in Phoenix A today were already active billions of years ago, establishing the framework within which all later structures evolved. Darkness has always been a tool of creation. The influence of Phoenix A extends even into regions where its direct radiation cannot reach. Gravity has no limit, and its pull organizes matter across the entire cluster. The orbits of galaxies, the flow of gas, even the shape of the cluster's gravitational potential, all bear the imprint of the central mass. In this sense, the black hole acts as an anchor, holding the cluster together. Without such a massive center, the combined motion of hundreds of galaxies might eventually tear the system apart. Instead, they orbit in a vast dance, bound by the invisible weight of the darkness at the core. When astronomers map the Phoenix cluster, they see this structure clearly. The galaxies form a roughly spherical distribution around the center, with densities decreasing outward. The hot gas fills the spaces between them, and the entire system is threaded by dark matter, the even more elusive substance that accounts for most of its mass. Phoenix A sits at the focal point of all these layers, its gravity and energy output shaping them simultaneously. Its influence is both local and global. It determines how gas moves near the core, and it helps define the gravitational balance of the entire cluster. The interplay between darkness and creation also manifests in the timing of cosmic events. The radiation from Phoenix A's past outbursts travels outward, heating distant regions of the cluster. Some of that energy reaches the outskirts only after millions of years, creating a delayed reaction that stabilizes the system long after the jets have quieted. Meanwhile, the gas closer to the center cools and begins to condense again, setting the stage for the next episode. The cluster operates like a slow engine, powered by cycles of input and output, each phase depending on the previous one. The black hole's darkness ensures that the rhythm continues. This pattern is echoed across the universe. Everywhere astronomers look, from nearby galaxies to distant quasars, they find signs of black holes influencing their surroundings. The scale varies, but the principle remains the same. Energy released near the event horizon shapes the larger structures around it. In small galaxies, this influence determines whether new stars can form. In massive clusters like Phoenix, it governs the temperature and distribution of gas across millions of light years. Darkness, operating through gravity and magnetism, becomes the sculptor of light. It's worth noting how indirect this creation is. Phoenix A doesn't build stars in the way a nebula does. It doesn't emit light that fuses atoms or form planets from dust. Its influence is structural, environmental. It sets the conditions that make such things possible. By heating, compressing, and redistributing matter, it ensures that the cluster remains active rather than collapsing into dormancy. It is an unseen hand that guides the visible universe, shaping without touching, controlling without acting in any deliberate sense. When viewed in this way, the contrast between darkness and creation becomes less about opposition and more about cooperation. The universe functions through balance. Every process has its counter-process. Cooling meets heating, collapse meets expansion, light meets shadow. The Phoenix cluster is one of the clearest manifestations of that balance. Its core glows because its heart is dark. The galaxies around it shine because the black hole regulates their growth. Without that interplay, the structure would fall apart or burn out. Observational evidence of this balance continues to grow. Instruments like the Chandra X-ray Observatory and the ALMA array capture data that allow scientists to quantify the energy exchange between the black hole and the cluster. They can see how the temperature of the gas changes over time, how the cavities inflate and rise, how the star formation rate fluctuates. These measurements reveal a consistency that seems almost self-correcting. When the gas cools too much, the black hole awakens. When it heats too much, it quiets down. No intelligence guides this cycle. It is simply the outcome of physics acting over enormous scales. The result, however, is a system that endures, constantly renewing itself through the interaction of light and dark. The notion that darkness can be creative runs counter to intuition. For centuries, humans associated darkness with absence, with what is missing rather than what is present. But in the universe, absence often carries the greatest influence. The void around a black hole is not empty. It is dense with curvature, energy, and motion. The regions of space we call dark are where gravity performs its most intricate work, weaving the invisible threads that hold everything together. Phoenix A is the embodiment of that principle, a presence so powerful that it defines its environment not by what it emits, but by what it withholds. On human timescales, these processes are almost static. The cluster changes too slowly for any observer to notice. Yet when we compress billions of years into a single mental image, we can see it move. The gas cooling, the jets igniting, the stars forming, the cavities drifting. The rhythm becomes clear. Creation emerging from control, order sustained by restraint. Darkness does not oppose light, it gives light form. Even as we observe from across 6 billion years of distance, the same balance continues. The photons reaching our telescopes carry the imprint of that interaction. In every wavelength, X-ray, optical, radio, we see the results of darkness shaping creation. The Phoenix cluster shines because its core restrains it, because its black hole transforms gravitational collapse into regulated growth. That relationship defines not just this one cluster, but the structure of the universe as a whole. And so, in the deep quiet of intergalactic space, where no sound travels and no light escapes the central void, the act of creation persists. Phoenix A, a black hole so vast it defies imagination, continues to influence the birth of stars and the temperature of gas. It does so without radiance, without noise, without intent. Its power lies in what it holds back, not what it releases. The darkness at its heart shapes everything that shines around it. There are black holes that feed furiously, their light blazing across the universe like a warning flare. And then there are black holes that fall silent, content to wait for the next wave of fuel to find its way inward. Phoenix A seems to live somewhere between those two extremes, a reluctant giant that could unleash almost unimaginable energy but, for now, appears to be resting. Its mass gives it the capacity for destruction on a cosmic scale, yet most of the time, it slumbers. When it does stir, the results ripple through millions of light years, but those moments are separated by long periods of calm. The most massive black hole we know of is also one of the most patient, and its patience is what defines the state of the Phoenix cluster today. The idea of a dormant or semi-dormant black hole might sound strange. These are objects born of collapse, famous for their appetite and the energy they release when they feed. But the truth is that most of the universe's supermassive black holes spend the majority of their lifetimes in quiet phases. Their feeding depends entirely on the availability of gas. When fresh material falls into the center of a galaxy, the black hole awakens, brightens, and launches jets of radiation. When that fuel runs out, it returns to a state of near invisibility. Phoenix A, despite its enormous potential, follows this same cycle. Its past activity is recorded in the cavities and shockwaves imprinted on the cluster's gas, yet at this moment in cosmic time, it seems to be between meals. Astronomers deduce this state not by seeing the black hole directly, but by measuring what isn't happening. The central galaxy of the Phoenix cluster is still forming stars, but at a reduced rate compared to earlier epochs. The jets that once inflated giant cavities now appear fainter. The X-ray glow of the surrounding gas suggests that the most recent outburst occurred hundreds of millions of years ago. The system bears all the marks of a black hole that has quieted down. It hasn't stopped feeding altogether, but it's operating in a low-power mode, drawing in just enough material to maintain its presence, without producing the spectacular eruptions that once defined it. This behavior raises interesting questions about how black holes regulate themselves. The same process that allows them to heat their surroundings also determines when they rest. When Phoenix A was most active, its jets injected vast amounts of energy into the intracluster medium, preventing the gas from cooling and cutting off its own supply of fuel. As the gas heated and expanded, less of it fell inward. The black hole effectively starved itself into dormancy. Now, as the gas slowly cools again, new filaments form and drift toward the center, setting the stage for a future awakening. This back-and-forth interaction ensures that neither extreme, overheating nor overcooling, persist for long. The giant restrains itself, reluctantly but inevitably, because physics gives it no other choice. If we could observe the central region of the cluster in real time, the transition between activity and quiescence would appear gradual, almost imperceptible. The glow of the accretion disk would dim, the jets would narrow, and the cavities in the gas would expand and rise away. Then, for millions of years, nothing dramatic would happen. The cluster would settle into equilibrium. Gravity and pressure would balance again, the hot gas would stabilize, and the galaxies would drift through their slow orbits as though nothing had changed. Only on timescales far longer than human history would the cycle become visible. Eruptions separated by ages of calm. Phoenix A's current quiet state gives astronomers a rare opportunity. Most observations of black holes come from their active phases, when the radiation they emit is strong enough to be detected across the universe. Dormant phases are harder to study, but they reveal how black holes interact with their environments when they are not dominating them. By examining the residual heat in the cluster's gas and the faint radio signatures left by past jets, scientists can estimate how long it has been since the last major outburst and predict when the next one might occur. The data suggest that Phoenix A is now in a period of relative stillness that could last for hundreds of millions of years, an intermission in a drama that has played out over cosmic time. Even at rest, though, a black hole of this size exerts influence. Its gravity continues to anchor the cluster, shaping the orbits of galaxies and the flow of gas. The heat it released in past eruptions still lingers in the intracluster medium, slowing cooling and preventing new starbursts from igniting too quickly. In this way, the black hole's earlier fury sustains the cluster's present calm. Energy and time trade places, one phase giving rise to the next. The reluctant giant may sleep, but its legacy does not. The difference between a dormant and an active black hole is a matter of perspective. For the cluster, even a quiet Phoenix A is active enough to maintain equilibrium. The faint trickle of accreting gas still produces heat, though far less than during peak periods. For us, observing from billions of light years away, that difference translates into changes in brightness too subtle to detect without precise instruments. Chandra's X-ray data and the observations from the Atacama Large Millimeter Array reveal faint signals that betray ongoing low-level activity, weak jets, residual magnetic fields, and gentle ripples in the gas. They are the last breaths of a system catching its balance before the next deep inhale. This kind of cyclical dormancy is a crucial part of how galaxy clusters evolve. Without it, feedback would be too violent, disrupting the delicate structure of the system. Phoenix A's restraint prevents the cluster from losing too much gas to heating, or too much stability to star formation. It's as though the black hole's immense power comes with an inbuilt mechanism for moderation. Whenever it acts, it plants the seeds of its own stillness. The reluctance isn't conscious, but the outcome is the same. Bursts of activity followed by calm, a pendulum swinging between extremes that together maintain the whole. To see how this pattern unfolds, scientists study the cavities left by older outbursts. These voids rise slowly through the cluster's plasma, carrying energy away from the center. As they rise, they expand and cool, transferring heat to the surrounding gas. Eventually they dissipate completely, but their motion helps distribute energy throughout the cluster. The distances between these cavities mark the intervals between outbursts. In the Phoenix cluster, that spacing suggests a rhythm, major eruptions separated by hundreds of millions of years. We happen to be observing it during one of the pauses between beats. The silence, though temporary, gives us a glimpse of the long-term balance that defines this system. From a broader perspective, Phoenix A's apparent reluctance reflects the universe's tendency toward moderation on grand scales. Extremes do not persist. Explosions fade, heat disperses, gravity reasserts control. The same principles that apply to stars and galaxies also apply to black holes. After every period of rapid growth comes a plateau. Energy is released, equilibrium restored, and the system begins again. The Phoenix cluster embodies this pattern perfectly. Its name, echoing the myth of rebirth, is fitting not just for its cycles of heating and cooling, but for the way its central giant alternates between fire and rest. Dormant phases are not truly inert. Even when it's quiet, Phoenix A continues to process small amounts of matter. Gas clouds occasionally drift close enough to be drawn in, producing faint flashes of radiation as they fall. These minor events remind astronomers that the black hole never really stops feeding. It simply operates at a lower efficiency. The hunger described earlier never vanishes. It just slows to a whisper. The black hole's accretion disk remains, faint but active, converting the slow trickle of infalling matter into steady warmth. That faint energy output may be enough to maintain the cluster's balance for millions of years without the need for a major eruption. There is a certain irony in how this works. The most powerful object in the cluster, capable of releasing more energy than all its stars combined, sustains itself by doing almost nothing. Its gravitational influence ensures that gas continues to flow inward at just the right pace to keep the system alive. This state of near equilibrium is fragile, but it can last for astonishingly long periods. It's the cosmic equivalent of a deep breath held for ages, waiting for the next exhale. To imagine what this might look like from a closer vantage point is to imagine stillness on a scale too vast for human senses. The central galaxy would glow softly, its halo of stars motionless to the eye. No flashes, no bursts of radiation, no visible jets, only the slow drift of gas illuminated by starlight scattered through the cluster. In the radio spectrum, faint echoes of earlier activity would still hum, like the afterglow of distant thunder. The space around the black hole would appear calm, but beneath that calm, magnetic fields would continue to twist, and gravity would continue to draw in particles, imperceptible one by one, but relentless over time. This quiet period offers a reminder that activity in the universe is never constant. Systems breathe in and out, alternate between chaos and order. For Phoenix A, the dormancy is as important as the eruption. Without the pauses, the system would burn itself out. Each resting phase allows the cluster to cool just enough for new material to form, ensuring that there will always be something left to feed the next outburst. The reluctance is part of the rhythm, not a deviation from it. In a sense, the current calm of Phoenix A represents maturity. In its earlier epochs, when the universe was younger and denser, it likely consumed material at a furious rate, growing rapidly from smaller beginnings. Those were its formative years, defined by constant collisions and abundant fuel. Now, billions of years later, it has reached a kind of stability. It has achieved a balance between appetite and restraint. It is powerful enough to dominate its environment without tearing it apart. Its reluctance is not weakness, but wisdom built into the laws of physics. This phase of quiet doesn't mean the story is over. The gas in the Phoenix cluster continues to cool slowly, and over time, more of it will condense into filaments that drift toward the center. When enough of that material accumulates, the black hole will awaken again. The next eruption may not occur for hundreds of millions of years, but when it does, it will once again reshape the cluster, reheating the gas, creating new cavities, and resetting the cycle. For now, though, the giant rests. Even in stillness, Phoenix A exerts a presence that can be felt through data, through models, through the faint patterns that mark its influence. It is a paradox in motion, an engine idling at near zero power, yet dominating the fate of everything around it. The reluctance isn't a pause in its story, it is the story. The cluster's galaxies continue to orbit, its gas continues to shimmer, and at the center, the most massive black hole we have ever found waits, immense, quiet, and necessary. When we observe it across billions of light years, what we see is not silence but balance. The heat from ancient eruptions still warms the gas. The gravitational field still holds galaxies in their courses. The absence of activity is not absence of power. It is power distributed perfectly. Phoenix A's reluctance is the universe's reminder that even the greatest forces must rest between acts, that creation and destruction require pauses between them. Somewhere in that stillness, the next weave of motion is already beginning, invisible but inevitable, waiting for its turn to rise. The universe is mostly silence, and yet, even silence can speak if you know how to listen. Phoenix A does not shout its presence across space. It whispers it through disturbances in temperature, faint ripples in X-rays, radio waves stretched thin by distance, and subtle imbalances in the glow of a cluster 6 billion light-years away. To study something that does not emit light, astronomers have learned to read these echoes, the residue of ancient activity still moving outward through the intracluster medium. Listening to Phoenix A is like eavesdropping on the past, because every photon, every vibration of energy that reaches us, began its journey long before there were humans to receive it. Those echoes exist across a wide range of frequencies. In visible light, the Phoenix cluster looks like a dense field of golden smudges, each one a galaxy. In X-rays, however, the image transforms into a smooth cloud with hollows and ripples, the direct signature of the black hole's ancient outbursts. Each hollow marks a region where jets once carved through the gas, each ripple a shockwave that has been travelling outward ever since. Even though the black hole may be quiet now, those waves still carry its story, like sound resonating long after the bell has been struck. Radio telescopes are particularly good at hearing these remnants. Arrays like the Very Large Array in New Mexico and the Australia Telescope Compact Array collect radio waves from the distant cluster and translate them into maps of synchrotron radiation, light emitted by electrons spiraling around magnetic fields. These electrons were accelerated by Phoenix A's jets millions of years ago. The patterns they form now trace the paths of those jets and reveal how the energy spread. To the trained eye, each contour in those radio maps is an echo, a record of movement frozen in space. At higher energies, observatories like Chandra and XMM Newton pick up the thermal response of the cluster's gas. When the black hole's outbursts passed through it, they left behind slight temperature differences. Hotter regions mark where the gas was compressed. Cooler regions show where it expanded. By measuring those gradients, scientists can reconstruct the power of the original eruption and how long it lasted. The process is similar to seismology on Earth. By studying the waves that travel through a medium, you infer the strength and nature of the source that produced them. Because light takes time to travel, observing the Phoenix cluster is also a form of time travel. The radiation that reaches us now began its journey when the solar system was still forming. Everything we detect is a delayed signal. If we could somehow see the cluster as it exists at this exact moment, 6 billion years later it might look quite different. Perhaps quieter, perhaps beginning a new cycle of activity. But what we have are its echoes, frozen records of what once happened, preserved in the cosmic background. The act of listening to the void is always an act of listening to history. In recent years, advances in radio astronomy have deepened that listening. Networks of antennas scattered across continents can now be linked through a technique called interferometry, effectively creating a single instrument the size of Earth. The Event Horizon Telescope used this method to image the shadow of a black hole for the first time. While Phoenix A is too distant for that level of resolution, the same principles allow scientists to map the cluster's radio lobes in detail. The more antennas that participate, the clearer the signal becomes, turning faint whispers into discernible structure. These observations have revealed that the Phoenix cluster is still resonating from multiple generations of eruptions. Older cavities float farther from the centre, while younger ones sit closer in. The spacing between them shows how often the black hole has cycled through active and quiet phases. It's a record of rhythm written not in sound, but in light stretched beyond human senses. When plotted in sequence, these cavities tell a story of repetition, outburst, expansion, rest, and renewal. The echoes are not random. They form a pattern, a heartbeat that continues long after the original pulse has faded. Even the cosmic background itself, the faint microwave radiation that fills the universe, carries traces of such interactions. When the hot gas in a cluster scatters those ancient photons, it slightly alters their energy, producing what's known as the Sunyaev-Zeldovich effect. Sensitive detectors can measure these minute distortions, effectively hearing the cluster's imprint on the oldest light in existence. In the case of Phoenix A, that effect is pronounced, confirming how dense and energetic its gas remains. Every frequency tells a piece of the same story, an invisible engine whose influence echoes through everything around it. To turn those data into understanding requires both technology and interpretation. The signals collected by telescopes are faint, often buried in noise. Astronomers spend months cleaning, calibrating, and cross-referencing them. They compare observations from different instruments, align the images, and look for correlations. A faint ridge in X-rays may line up with a contour in radio emission. A drop in brightness may match the location of a cavity. Piece by piece, the echoes assemble into a coherent picture. What emerges is not a single moment, but a timeline spanning hundreds of millions of years. In that timeline, Phoenix A appears less like a monster and more like a slow, breathing system. Each outburst sends energy outward, which eventually fades and is replaced by the next. The echoes we detect now are part of a sequence that never really stops. Even when the black hole falls silent, the cluster continues to vibrate with the memory of its activity. The gas moves, the temperature shifts, and the gravitational field adjusts. To listen to the void is to realize that the universe never truly rests. It only changes its volume. There's something almost intimate about the way we receive these signals. The photons that left the cluster billions of years ago arrive one by one, striking detectors on Earth or in orbit. Each carries a fragment of information about its source. Collected together, they allow us to reconstruct the events of an age long gone. It's a process that feels both mechanical and poetic. Machines built by human hands, catching the faintest whispers of a cosmos so vast that we can only glimpse its echoes. In those data streams, noise becomes knowledge. The more we refine our instruments, the more sensitive our hearing becomes. New radio arrays, like the Square Kilometre Array, now under construction, will have enough sensitivity to detect even weaker emissions from clusters like Phoenix. future X-ray observatories will map temperature variations in greater detail, revealing the fine structure of the shock waves that ripple through the gas. Each improvement in resolution brings the void into sharper focus, showing that emptiness is not silent after all. It's easy to forget when looking at false colour images of the Phoenix cluster that those colours represent invisible wavelengths. Our eyes are blind to most of what the universe emits. What we call listening in this context is really translation, turning frequencies beyond human perception into forms we can interpret. In radio astronomy, that translation can be literal. The data can be converted into audio, compressing millions of years into seconds. The resulting sound is a deep, droning hum, sometimes punctuated by faint beats where the signal intensifies. When scientists have done this with data from other clusters, the results have been eerie and beautiful. Phoenix A's own song would likely be similar. A low, continuous vibration, the sound of space itself resonating with energy released by darkness. Beyond the data, listening to these echoes changes how we think about time. Every observation is a conversation with the past. The signals we record today are answers to questions asked by events that happened before our species existed. The void is not empty but full of responses, waiting for technology sensitive enough to hear them. This awareness transforms the act of observation into something more than measurement. It becomes participation in a dialogue that spans the history of the universe. Through these echoes, we also catch glimpses of how energy moves through cosmic ecosystems. The waves of heat and radiation emitted by Phoenix A influence the formation of stars in its cluster, the cooling of gas, and even the structure of magnetic fields. Those processes in turn generate new emissions that may one day be observed as future echoes. The system loops back on itself endlessly. Nothing that happens in the cluster ever truly disappears. It simply shifts to a different form of signal. Even with all this information, much remains hidden. The deepest regions near the event horizon produce emissions too weak or too absorbed to reach us. We know they exist only through inference. The silence from those zones is part of the message too, a reminder that not all knowledge can be retrieved. Some parts of the void remain genuinely quiet, perhaps forever. Yet even that absence helps define the whole. To listen to the universe is to accept that some notes will always be missing. Still, the listening continues. Night after night, arrays and observatories turn toward the Phoenix cluster, collecting photons that began their journey eons ago. Each addition to the data archive adds depth to our understanding, refining the models that describe how black holes interact with their environments. The process is cumulative and patient, much like the phenomena it studies. The echoes we hear today may one day guide observations of clusters even farther away, where the first giants of the universe are still forming. In a very real sense, the void is not silent at all. It is filled with the after-sounds of creation and the memory of energy released by objects like Phoenix A. We listen across space and time, catching fragments of those memories as they drift through the cosmos. Every faint signal is a message that says the universe once moved here, once burned here, once changed here. The black hole itself may be silent, but its surroundings are an orchestra of consequences, and so the listening continues, not for noise, but for meaning hidden within the quiet. Phoenix A's echoes remind us that even the darkest corners of existence can leave traces bright enough to study. The cluster hums, the gas vibrates, and from across billions of years we hear it. The sound is faint, patient and endless, the universe speaking softly about its own history through the long, low echoes in the void. When you try to imagine Phoenix A, the numbers quickly escape the mind's grasp. They are too large, too distant, too far removed from anything we experience. 100 billion suns compressed into a region smaller than our solar system, jets extending for hundreds of thousands of light years, a cluster so vast that even light needs millions of years to cross it. The human brain wasn't built to hold these scales comfortably, yet astronomy requires that we try. to understand the universe is to stretch perception until it can hold both the very small and the very large at once, until numbers stop feeling impossible and start feeling like context. Phoenix A exists to test those limits. It is an object so immense that its mere existence rewrites our sense of proportion. If you could somehow set the Phoenix cluster beside our own Milky Way, the difference would be almost absurd. The Milky Way spans about 100,000 light-years, containing a few hundred billion stars. The Phoenix cluster stretches across millions of light-years, and its central black hole outweighs the one at our galactic centre by a factor of 25,000. Sagittarius A, the black hole at the heart of the Milky Way, is massive enough to govern our galaxy, but compared to Phoenix A, it's a pebble orbiting a mountain. Even the largest stars we know, supergiants like Betelgeuse or UY Scuti, would be invisible specks if placed near it. These comparisons are not meant to shrink our significance, but to illuminate how the same physical laws apply across every scale. The same gravity that holds the Moon in orbit around Earth also binds galaxies into clusters. The same atomic forces that power our Sun shape the evolution of the brightest quasars. Phoenix A follows the same equations as every other object in the universe. It simply operates them at the highest possible settings. Its scale magnifies what smaller systems reveal in miniature. To appreciate that, it helps to walk through the scale step by step. Start with something familiar. The Earth, about 13,000 kilometers across. Our Sun is 100 times larger, its diameter about 1.4 million kilometers. The distance from Earth to the Sun is 150 million kilometers, a unit we call 1 astronomical unit. The edge of our solar system, where the influence of the Sun's gravity begins to fade, lies about 100 times farther still. And yet, if we were to place the event horizon of Phoenix A in the same frame, it would easily encompass all of that and more. The black hole's radius, known as the Schwarzschild radius, is estimated to be hundreds of billions of kilometers. That is hundreds of times larger than the orbit of Neptune, large enough to swallow our entire solar system and leave room for thousands more. It's almost meaningless to call something like that large, because large implies comparison. Phoenix A operates in a regime where comparison itself falters. Even light struggles to articulate its size. At the speed of light, it would take days to travel from one edge of its event horizon to the other. On a human timescale, that means the black hole could spin once in a week, dragging space-time around with it like water swirling down a drain so deep that the drain itself bends reality. When scientists describe scales like these, they often use units that exist only to make the numbers survivable. Light years, parsecs, solar masses, each as an attempt to compress incomprehension into notation. Phoenix A's mass is about 100 billion solar masses, but the word solar mass itself is a human invention, chosen because it gives us a baseline. It's a way of saying, imagine the Sun, the most dominant object in our lives, and then multiplied 100 billion times. Even that image fails, but it's the best bridge we have between imagination and reality. The Phoenix cluster itself is another leap outward in scale. It contains hundreds of galaxies, each with hundreds of billions of stars, all orbiting a common centre of gravity. The entire structure spans millions of light years and holds more mass than could ever be counted. Its hot gas, the plasma that fills the space between galaxies, contains more matter than all its stars combined. When we say Phoenix A sits at the centre, we don't mean it occupies a position like the Sun in our solar system. We mean it defines the gravitational architecture of the cluster. Everything moves in relation to its invisible weight. Scale in the universe works like nested patterns. Every level contains echoes of the levels above and below. The structures we see at the largest scales, clusters, filaments, voids, mirror the patterns of smaller systems. Stars orbiting galaxies, planets orbiting stars, electrons orbiting nuclei. The repetition is not perfect, but the geometry of motion persists. Phoenix A is part of that pattern, the extreme node in a network of gravitational relationships. Its jets stretch outward like threads connecting galaxies, its energy radiating through the medium like vibrations on a cosmic web. Even time itself scales differently near such an object. The gravitational field around Phoenix A is so intense that it dilates time dramatically. To an observer near its event horizon, seconds would stretch into years relative to someone far away. If you could somehow watch matter orbiting near the edge, you would see it move in slow motion, its clock running thousands of times slower than yours. The curvature of space and time becomes a unit of scale as real as distance or mass. What we call large here isn't just physical, it's temporal, experiential, woven into the way the universe measures itself. One of the most challenging aspects of studying black holes is that our instruments, no matter how advanced, always look at them from outside. We can never peer beyond the event horizon. All we can do is measure the consequences of what lies within. Yet even that limitation tells us something about scale. The boundary of a black hole represents not just the limit of light, but the limit of observation itself. Phoenix A is so massive that it creates a region where measurement ceases to have meaning. It marks the line between the knowable and the permanently hidden, a scale beyond which the concept of inside loses definition. That idea echoes far beyond astrophysics. Every field of science has its own horizons, points beyond which our tools and models stop working. In physics, it's the Planck scale on the small end and black holes on the large. In biology, it's the complexity of consciousness. In cosmology, it's the boundary of the observable universe. Phoenix A sits near the outer limit of what we can understand not because it's physically unreachable, but because its scale collapses the distinction between theory and reality. It turns equations into phenomena. It makes abstract curvature into visible shape. To measure such an object requires telescopes that themselves embody vast scales. The Chandra X-ray Observatory orbits Earth at a distance of tens of thousands of kilometers. The Atacama Large Millimeter Array spreads across the desert of northern Chile, its antennas separated by miles but working together as one instrument. Each piece of data they collect, each photon or radio wave, is a microscopic fragment of an enormous puzzle. Scientists spend years combining those fragments into maps that can describe how energy moves across millions of light years. The act of measuring Phoenix A mirrors the object itself, something immense constructed from many smaller parts. Perhaps the most humbling aspect of scale in astronomy is that everything we observe, no matter how large, remains only a small piece of a larger whole. The Phoenix cluster is part of a supercluster, which is part of a filament, which in turn is part of the vast cosmic web stretching across the universe. Even the largest black hole we've found is just one node in that structure. The same forces that shape galaxies also shape the universe itself. Scale doesn't just measure size, it measures connection. When astronomers speak of scales like billions of light years or hundreds of billions of solar masses, it can be tempting to treat those as abstractions, but each number represents something tangible. A light year is a measure of distance, but also of time. The mass of the Sun is a measure of gravity, but also of potential energy. Phoenix gathers all these measures into one object, a kind of cosmic ledger where every unit of scale is pushed to its limit. In it, we see how the universe organizes itself, through hierarchy, symmetry, and proportion. And yet, despite its enormity, Phoenix A still obeys the same physics that govern everything else. The difference between it and a black hole formed from a collapsing star is merely one of degree, not of kind. That continuity across scales is what makes the universe readable. It means that by studying the small, we can infer the large. The spin of an electron and the spin of a galaxy obey the same conservation laws. The curvature of space-time around Earth and the curvature around Phoenix A follow the same equations. The scale changes, but the rules don't. Understanding those scales also puts our own existence into perspective. On Earth, gravity feels weak. It keeps our feet on the ground, but it can be overcome by a leap or a gust of wind. In a cluster like Phoenix, gravity is the only story. It sculpts everything, dictates the motion of entire galaxies, defines the boundaries of light itself. Yet the same force binds our world to the sun. When we look at Phoenix A, we're not seeing something alien, but a reflection of the same laws that made us. Scale connects rather than separates. That connection becomes clearer when we think of the universe as a continuum of scales rather than a hierarchy. From quarks to stars, from atoms to clusters, everything participates in the same framework of energy and matter. The universe writes itself in scale, not in categories. Phoenix A is a letter written in the largest possible font, a demonstration of what gravity can do when given enough time and material. Reading it requires patience, but the language is familiar. Even our attempts to describe such immensity are acts of translation across scale. Every telescope, every simulation, every scientific model reduces something enormous to human terms. We turn light into data, data into images, images into understanding. We compress billions of years into seconds of visualization, millions of light years into diagrams on a screen. The process is imperfect, but it's what allows us to think about phenomena like Phoenix A at all. The universe is written in scales too vast to experience directly, so we build tools to read it piece by piece. In the end, what we find in Phoenix EA is not alien gigantism, but the familiar structure of physical law stretched to its outer limits. The scale may be beyond imagination, but the behavior is recognizable. Attraction, rotation, release, balance. The same dynamics that shape our solar system operate there, magnified until they become the architecture of a cluster. This realization carries its own quiet comfort. The cosmos may be vast beyond comprehension, but it is not chaotic. It follows patterns, ratios, and rhythms that connect the smallest grain of dust to the largest black hole. So when we speak of a universe written in scale, we're speaking of a continuity that includes everything, from the photons arriving at your eyes to the jets of Phoenix A still pushing through the cluster's gas. Scale is not a measure of separation, but of unity. It's the way the universe tells one story in different sizes. Phoenix A, immense and invisible, is one of the largest sentences in that story. And though it dwarfs everything we know, it still belongs to the same language, the same physics, the same quiet order that begins here, where we stand, looking up and trying, in our small way, to read. Light defines what we see, but shadow defines what light means. The two are inseparable, opposite yet dependent, and nowhere in the universe is that relationship clearer than around a black hole. Phoenix A, the largest black hole we've ever found, lives in a state where light and shadow are locked together, one giving shape to the other. It is a region where light bends so completely that it circles back on itself, where brightness originates from the edge of darkness, where the boundary between illumination and absence becomes not just blurred but interchangeable. To understand Phoenix A, you have to understand that light and shadow in the universe are not moral contrasts or symbols of good and evil. They are physical states, and sometimes the darkest places are the only ones bright enough to see. In every image of the Phoenix cluster, the light tells a story written by the black hole's shadow. The glow of X-rays tracing the hot gas, the faint radio lobes marking ancient jets, the optical shine of billions of stars, all of them are the result of processes that begin in darkness. The energy that lights the cluster originates from matter falling towards something invisible. Each photon we detect was once part of material that spiraled close to annihilation. The light exists because the shadow consumes. Phoenix A turns destruction into illumination, feeding on gas and returning the energy in the form of radiation, heat, and structure. It's a paradox that pervades the universe. What disappears into shadow makes light possible elsewhere. The term black hole itself is misleading. It suggests a void, an absence, a hole in space. In reality, a black hole is more like a furnace sealed inside a boundary that nothing can cross. The interior may be hidden, but the space just outside, the event horizon, is the most luminous place in the universe. As matter falls in, it heats up, radiating light across every wavelength. For smaller black holes, that light can outshine entire galaxies. For Phoenix A, the energy is so immense that even a low level of activity affects millions of light-years of space. The shadow's edge glows, and that glow becomes a signature visible across the cosmos. Light near a black hole doesn't travel in straight lines. Gravity curves space-time, bending the paths of photons. Some light escapes directly, but much of it circles around, looping near the event horizon before finding an exit. This bending creates what scientists call a gravitational lens. The light from stars and gas behind the black hole is distorted, forming arcs and rings. When we observe the Phoenix cluster, part of what we see is not the cluster itself, but the warped reflection of what lies beyond it. The shadow acts as a mirror for distant light, shaping how the universe reveals itself to us. This relationship between light and shadow also defines our limits of understanding. Every observation we make of Phoenix A is based on the light it indirectly produces, the X-rays from heated gas, the radio waves from its jets, the starlight affected by its gravity. We never see the black hole itself. The very thing that defines the system remains hidden, existing only as an inference. That invisibility isn't a failure of technology. It's a fundamental property of nature. The universe keeps its deepest mechanisms behind a curtain of shadow, but from the movement of light, we can still deduce what must be there. The shadow becomes not an absence of knowledge, but a map of the unknown. The paradox extends beyond black holes. Everywhere we look in the cosmos, we find that darkness and light coexist in the creation of structure. Stars form in molecular clouds so dense that visible light cannot escape. Galaxies rotate within halos of dark matter that emit no light at all. Even the expansion of the universe is driven by something we call dark energy, a name that simply means we don't understand it yet. Light reveals, but darkness sustains. Without shadow, there would be no contrast, no shape, no gravity to bind the bright things together. In Phoenix A, this interplay takes on its most extreme form. The gas in the cluster glows because of energy released by matter plunging into darkness. The cavities carved by jets are voids filled with the relic light of past eruptions. The bright filaments of new stars forming in the central galaxy exist because the black hole heated the gas just enough to delay collapse, allowing it to condense in smaller, more controlled regions. Every visible feature of the cluster, the stars, the plasma, the light, owes its shape to something invisible. The shadow organizes the brightness. If you trace that logic far enough, it reaches into philosophy. Humans have long associated light with knowledge and darkness with ignorance, but the universe doesn't respect that division. In cosmic terms, we learn the most by studying what we cannot see. Our understanding of gravity, relativity, and quantum mechanics has advanced precisely because black holes hide their interiors. The shadow forces us to infer, and in doing so, it teaches us. The paradox is that the universe's most mysterious objects have given us the clearest insights into how reality works. Phoenix A, though unseen, expands the boundary of what can be known simply by existing. The physics behind this paradox are precise. As matter approaches the event horizon, it releases gravitational energy. A small fraction of that energy escapes as radiation, while the rest is carried inward beyond the point of return. The escaping light is the last visible record of the process, the final message before silence. In effect, the shadow writes in light what it cannot say directly. That's why the space around black holes shines so fiercely even as the interior remains black. It's a transaction between visibility and oblivion. One region brightens because another vanishes. For astronomers, this interplay is both a challenge and a guide. Every time they observe Phoenix A, they must separate what is intrinsic from what is reflected or distorted. The bright gas clouds, the shock fronts, the faint halos of radiation, all are manifestations of the black hole's presence, but none are the black hole itself. By studying how light behaves near it, scientists can map the structure of space-time, measure the spin, and estimate the mass. They read the shadow's handwriting by tracing how it bends light. The same principle that makes direct observation impossible becomes the tool that allows indirect discovery. On a deeper level, the paradox of light and shadow mirrors the way the universe conserves balance. Energy never disappears, it merely changes form. Light emitted from one place is absorbed in another. Heat radiated by collapsing matter becomes the glow of surrounding gas. The death of one system seeds the birth of another. Darkness, in this sense, is not destruction but transformation, the passage of energy through hidden stages. Phoenix A embodies that process continuously. What it swallows returns to the cosmos as radiation, motion and structure. The shadow recycles light. Even on Earth, we participate in that exchange without noticing it. The atoms in our bodies were forged in stars, scattered into space and drawn into new systems under gravity. The light we see from distant galaxies left its source before our planet formed, and the energy it carries now warms our instruments and our eyes. The cycle of light and shadow that defines Phoenix A also defines us. We are built from the remnants of past stars, organized by the same physics that govern black holes. The paradox is not distant. It is the structure of everything. If we could watch Phoenix A from a vantage point nearby, we would see the paradox in motion. Gas swirling toward the center would brighten until it vanished. The region around the event horizon would shimmer with light being bent and re-emitted in every direction. Farther out, the jets would glow as electrons spiraled through magnetic fields, their light gradually fading into the radio spectrum. The scene would look violent, but in its slow unfolding, it would also be serene, a steady exchange of light and shadow, maintaining cosmic balance. The paradox also defines how time flows near the event horizon. From our perspective, matter approaching the black hole seems to slow down, its light redshifting as it fades from view. From its own perspective, it crosses the horizon in finite time. To us, the process never finishes. To it, the process ends instantly. The same event contains both eternity and immediacy, both fading light and vanishing shadow. The boundary between perception and reality becomes as blurred as the boundary between bright and dark. Over the years, astronomers have tried to visualize this balance. Computer simulations show light bending into rings, photons circling multiple times before escaping. These images, based on Einstein's equations, reveal that even pure light cannot escape the geometry of gravity. The brightness we see near the event horizon is partly light from behind it, wrapped around by space-time. The shadow, in that sense, contains its own reflection. Phoenix A may be far too distant to image in such detail, but the same principles apply. What we see of it is already both presence and absence, emission and distortion. When you step back and think of the Phoenix cluster as a whole, the pattern repeats. The bright galaxies exist within a background of darkness. The visible matter, stars, gas, planets, is only a small fraction of the total mass. The rest is dark matter, unseen but dominant. The light of the cluster outlines its shadow, and the shadow holds it together. Even at the scale of the cosmos, visibility is a rare thing, a thin surface over an ocean of invisibility. Understanding that balance changes the way we think about the universe. It's tempting to value light for its clarity and to dismiss darkness as void. But the universe doesn't make that distinction. Light without shadow is blinding. Shadow without light is meaningless. Together they produce contrast, structure, and knowledge. The very act of seeing depends on what we cannot see. Phoenix A as a physical object embodies that principle. It turns invisibility into influence, silence into presence. From our distance, we receive only the faintest traces of that interplay, but they are enough. The photons captured by our telescopes are the echoes of a process that unites both light and shadow in one continuous exchange. The cluster glows because the black hole absorbs. The more material falls inward, the more the surroundings shine. It is an equilibrium written in opposites, proof that the universe's brightest moments are often born at the edge of darkness. To call that a paradox is merely to acknowledge that we stand inside it. We exist in the space between light and shadow, illuminated by energy that once belonged to something else, sustained by a balance we barely notice. Phoenix A is a reminder that those opposites are not enemies but partners. The shadow gives the light its shape. The light gives the shadow its meaning. Together they build the universe we see, a universe where even the darkest heart can shine. The Phoenix cluster is ancient, but the forces that shaped it began long before galaxies ever existed. To study it is to trace echoes that lead back to the dawn of time, to an era when the universe was still a blur of gas, gravity, and possibility. The light we see from it today left more than 6 billion years ago, but the story of Phoenix A, its colossal black hole, begins far earlier, close to the universe's own childhood. Every atom of gas it consumes, every ripple of gravity it creates, carries information about the first structures that emerged from the cosmic dark. In that sense, Phoenix A is not just an object of the present, it is a message from the past, a whisper from the beginning of time. When the universe was young, it was almost perfectly smooth. The Big Bang filled space with energy and matter, but everything was nearly uniform. Only tiny irregularities, fluctuations in density barely 1 part in 100,000, broke that smoothness. Over billions of years, those small differences grew under gravity's pull, forming the first stars, the first galaxies, and eventually the clusters that fill the cosmos today. Phoenix A sits at the end of that long chain of evolution. Its existence tells us that those early fluctuations must have produced regions dense enough to collapse into black holes almost immediately after the first light appeared. Without such early seeds, a black hole this massive could not exist now. Astronomers still debate how such seeds formed. One possibility is that the first black holes were born from the deaths of the very first stars, enormous short-lived giants made of hydrogen and helium. When they collapsed, they left behind cores tens or hundreds of times more massive than our Sun. Over time, through mergers and accretion, those cores could have grown into the supermassive black holes we see in galaxies today. But Phoenix A's size challenges that scenario. To reach 100 billion solar masses in just a few billion years, it would have needed a head start far beyond what stellar collapse alone could provide. That leads to another hypothesis: direct collapse. In this second model, vast clouds of primordial gas collapse directly into black holes without forming stars first. Under the right conditions, low turbulence, low metallicity, and rapid cooling, a single gas cloud could have imploded under its own weight, creating a black hole with a mass of 100,000 suns or more. Those early giants would then have served as seeds for the supermassive black holes that followed. If Phoenix A's origins lie in such a process, it represents a lineage that began almost as soon as the universe became transparent, when matter and light first decoupled and the cosmic background radiation we see today began to travel freely through space. That background radiation, the faint afterglow of the Big Bang, still fills the universe. When we observe it with instruments like the Planck satellite, we see patterns, minute variations in temperature that correspond to the earliest density fluctuations. Those patterns are the ancestors of structures like the Phoenix cluster. Each tiny bright or dark spot in the cosmic microwave background marks a region where gravity was slightly stronger or weaker, where matter would eventually gather or disperse. Over billions of years, those differences grew, and some became the sites of massive clusters anchored by black holes like Phoenix A. The whispers from the beginning of time are still there, encoded in that faint radiation, connecting the earliest moments of the universe to the structures we observe today. As the first black holes formed, they began to influence their surroundings almost immediately. Even at small scales, accretion and radiation from those early giants heated and ionized the surrounding gas, affecting how nearby stars and galaxies evolved. This process, known as cosmic feedback, started the same dance between light and shadow that continues in systems like Phoenix A. The early universe was far more crowded than it is now, galaxies forming and merging at a frantic pace, collisions feeding central black holes and triggering bursts of star formation. Over time, those mergers built the massive elliptical galaxies that dominate clusters today. Phoenix A's host is one of those, an ancient relic assembled from countless earlier systems, each one adding to the black hole's growth. When astronomers look at clusters like Phoenix, they also look backward through the timeline of cosmic structure formation. The hot gas that fills the cluster still carries the chemical fingerprints of early generations of stars. Elements like iron, oxygen, and silicon were forged in the cores of massive stars and spread through space by supernova billions of years before the cluster fully formed. The gas in the Phoenix cluster contains those elements in abundance, meaning that the material Phoenix A feeds on today is the product of ancient stellar life cycles. Even as it consumes, it digests history. Each atom of metal-rich gas tells a story of explosions that occurred long before our sun existed. By studying the composition of that gas, scientists can estimate when and how quickly the cluster's galaxies formed their stars. The ratio of heavy elements to lighter ones indicates how many generations of stars have lived and died. In Phoenix, those ratios suggest a long and complex history of formation, stretching back nearly to the beginning of cosmic time. The presence of a black hole as massive as Phoenix A confirms that gravity began organizing matter into immense structures very early in the universe's life. The whispers we detect now, in X-rays, in radio, in light stretched red by expansion, are fragments of that ancient process, still echoing across space. On the larger scales, the growth of structures like the Phoenix cluster follows the framework of the cosmic web. After the Big Bang, matter didn't distribute evenly, but instead flowed into filaments, long, thin threads of galaxies and gas separated by vast voids. At the intersections of those filaments, gravity gathered material into clusters. The Phoenix cluster occupies one of these intersections, a node in a network that spans the entire observable universe. The gas flowing into it along the filaments continues to feed its galaxies and, indirectly, its central black hole. Every cluster, every filament, is a fossil of the early universe's geometry, a preserved record of how gravity sculpted the first forms out of near uniformity. Even time itself carries those whispers. The red shift of the Phoenix cluster, the stretching of its light due to the expansion of the universe, tells us not only how far away it is, but how fast the universe has been expanding since that light began its journey. By comparing such measurements across many clusters, astronomers can reconstruct the history of cosmic expansion and infer the influence of dark energy. In that sense, each observation of Phoenix A adds another data point to our understanding of the universe's evolution. The cluster doesn't just sit in space, it sits in time, marking a moment when the universe was roughly half its current age, when structure formation had reached a mature but still dynamic stage. The idea that a black hole could serve as a time capsule might seem counterintuitive. After all, it swallows everything that comes too close. But the effects it leaves behind, its radiation, its jets, its influence on surrounding matter, carry information about the conditions that produced it. When scientists model Phoenix A's growth, they're effectively reconstructing a timeline of the universe itself. Each burst of activity corresponds to an epoch in cosmic history. The current calm phase reflects the long, slow expansion that has followed the universe's most active period of star and galaxy formation. The black hole's behaviour mirrors the universe's rhythm: violent beginnings, gradual settling, cycles of energy and stillness. Listening to those ancient whispers requires translating faint signals into meaning. The X-rays emitted by the cluster's gas reveal its temperature, which in turn tells us how deeply it sits in its gravitational well. The distribution of galaxies within the cluster traces how matter has flowed under gravity since the early universe. The shape of the radiolobes left by Phoenix A's past jets shows how energy moved through that environment. Each data set is a different form of whisper, carrying a different accent of the same story. Combined, they speak of a universe that has been building complexity from simplicity for more than 13 billion years. At times, the scale of that history can make the present moment feel small, but the connection runs both ways. When we detect a photon that left the Phoenix cluster 6 billion years ago, we become part of that timeline. The act of observation closes the distance between then and now. The universe is not separate from its observers, it is continuous, and every act of seeing brings the past into the present. The whispers from the beginning of time reach us not as distant echoes, but as living information. They are the evidence that the early universe is still speaking through the structures it left behind. What they tell us, above all, is that creation was never a single event. The Big Bang was a beginning, but not the whole story. The universe has been creating ever since, through gravity assembling clusters, through stars forging elements, through black holes releasing energy that regulates the flow of matter. Phoenix A is part of that ongoing creation, a participant in a process that began with the first fluctuations in the cosmic background. Its existence proves that even in a universe that began in uniformity, complexity was inevitable. As we listen to those whispers, we're also listening to our own origins. The same laws that shaped Phoenix A shaped the Milky Way. The same early gas that flowed into the cluster flowed into the regions that became our galaxy. The same gravitational patterns that organized its stars organized ours. We are not distant spectators. We are made from the same materials, governed by the same physics, and connected by the same cosmic history. The whispers from the beginning of time reach every atom of us, and so, the Phoenix cluster stands as both monument and message. It marks how far the universe has come and how deeply its first moments still resonate. The light that reaches our telescopes today began its journey when the cosmos was young, yet it carries the memory of even older beginnings. Phoenix A continues to feed, to influence, to radiate, to remind us that the universe remembers its own creation in every structure it forms. The whispers from the beginning of time are not fading. They are still unfolding, still speaking, carried in light, in matter, and in the silent gravity that binds them all together. Stars are not eternal. They burn, they age, and eventually they fade. Galaxies too live out long lives defined by those same stars, by their births, their deaths, and the spaces in between. In the Phoenix cluster, this process unfolds on a scale so immense that it becomes almost imperceptible, like a slow breath drawn across billions of years. What we call stillness is only motion too vast for us to feel. In the presence of Phoenix A, where gravity rules with the quiet authority of time itself, stars live and die according to rhythms set not by their own fusion, but by the balance between light and shadow at the cluster's core. When one star dims, another ignites, and together their collective glow becomes the pulse of galaxies dreaming in their long sleep. Every galaxy in the Phoenix cluster contains its own population of stars, young, old, and dying. The oldest are ancient, formed when the universe was still finding its equilibrium. They glow faintly, red and steady, their fuel nearly gone. The youngest are blue and hot, scattered along filaments of cooled gas near the central galaxy, born from material that condensed under the influence of the black hole's regulation. Phoenix A determines when and where that condensation can happen. By heating and cooling the gas in cycles, it dictates the timing of stellar creation. It is not a deliberate act, but an inevitable one. Gravity and heat play against each other, and stars are the result. The stars themselves live predictable lives, though the scales differ by orders of magnitude. The smallest burn for trillions of years, the largest for only millions. They fuse hydrogen into helium, then heavier elements as they age, building the chemical diversity that makes planets and life possible. In the Phoenix cluster, where star formation occurs in bursts triggered by the black hole's cycles, many stars are born in clusters of their own, packed together in regions of dense gas. These stellar nurseries blaze briefly before dispersing, leaving behind the remnants that enrich the surrounding medium. Each generation adds to the cluster's complexity. The slow accumulation of the heavy elements changes the chemistry of the gas, making future stars and planets different from the ones before. At the heart of this system, Phoenix A's influence extends like a clock that marks time in epochs instead of seconds. When the black hole erupts, its jets inject energy into the surrounding gas, halting new star formation. When it quiets, the gas cools and condenses, and new stars begin to form again. Over billions of years, this push and pull creates waves of stellar birth and death that ripple through the cluster. It's a kind of breathing, creation and pause, expansion and rest. In this rhythm, galaxies live their long lives, their light slowly fading as their fuel diminishes. The galaxies in the Phoenix cluster are mostly elliptical, their shapes smoothed by countless mergers. They lack the graceful spirals of younger systems, but they carry a richness of history instead. Each one is a collection of millions of past collisions, of stars consumed and reborn. Their combined light is a soft, diffuse glow that fills the cluster with a faint golden hue. In that light, the story of the universe's aging is written clearly, a transition from youth to maturity, from bright, active galaxies to older, quieter ones that now drift in equilibrium around the cluster's centre. The sleep of stars becomes the dream of galaxies, their gradual fading into stability, the quiet after the storm of creation. In the central galaxy, the relationship between starlight and black hole is most direct. There, cold filaments of gas stretch across tens of thousands of light years, weaving through the glowing core. Along those filaments, new stars are still forming, but at a measured pace. Each one will burn for millions or billions of years, contributing its light to the central halo before eventually returning its matter to the cluster as dust and gas. The cycle continues: birth, radiance, decay, and return. The galaxy's glow is sustained not by endless creation, but by the recycling of its own remnants. It's easy to imagine the Phoenix cluster as static, frozen in its immense stillness, but in truth, every star within it is changing. The faint red giants that dominate its light are nearing the end of their lives. Many will shed their outer layers, forming planetary nebulae before collapsing into white dwarfs. Others, the more massive ones, will end in supernova, scattering heavy elements and leaving behind neutron stars or black holes of their own. These smaller black holes may one day merge, adding their mass to the cluster's gravitational field and perhaps, over incomprehensible timescales, even to Phoenix A itself. The process is slow, but relentless. The cluster is not dying, it is transforming. The sleep of stars is not the same as death. It's a period of rest built into the physics of energy. As stars age and fade, their light lingers, travelling outward, contributing to the background glow of the cluster. Even after a star is gone, its photons continue across space, carrying its presence forward. That light may eventually reach distant galaxies, or our own telescopes, long after the source has cooled. The dreams of galaxies are made of that lingering light, the memory of stars that once burned within them. When we look at the Phoenix cluster, we are seeing not just the present, but the cumulative radiance of everything that has ever happened there. In the long future, the balance will shift again. Star formation will slow as the gas supply thins. The cluster's galaxies will grow redder and dimmer, their bright young stars replaced by long-lived embers. Over tens of billions of years, new generations will become rare. Eventually, the light will fade to a faint glow, and the galaxies will enter a phase of true rest. Yet even then, the process will not end. White dwarfs will cool into black dwarfs, releasing their remaining heat over trillions of years. Occasional collisions will ignite new flares of light, brief sparks in the long night. The Phoenix cluster's stars will sleep, but the dreams will continue in the slow exchange of energy and motion. Phoenix A will remain through it all, its hunger undiminished, its gravity constant. It will continue to anchor the cluster even as the stars fade. Over time, it may consume the remnants of those that wander too close, incorporating their mass into its own. The light of the galaxies may fade, but the dark center will persist. The name Phoenix is fitting because it describes a pattern that extends beyond life and death, renewal through transformation. Every outburst, every collapse, every generation of stars is part of that cycle. The cluster doesn't simply decay, it changes form, conserving its energy in new configurations. What makes this process remarkable is how it mirrors the life of the universe itself. On the grandest scale, the cosmos is also aging. Star formation peaked billions of years ago and has been declining ever since. The galaxies of the present are quieter than their ancestors, their light softer, their activity subdued. The universe is entering a phase of cosmic maturity, the same way the Phoenix cluster has. But maturity is not emptiness, it's the settling of energy into balance. The sleep of stars and the dreams of galaxies are the universe learning to rest without disappearing. In this rest lies continuity. The energy released by dying stars becomes the heat that keeps interstellar gas from cooling too quickly. The metals they produce seed new worlds in other galaxies. Even when the visible light fades, the memory of that light persists in radiation, in motion, in structure. Gravity continues to weave the remnants into patterns, ensuring that nothing is truly lost. The cluster's stillness is filled with unseen motion, the quiet hum of particles exchanging energy across time. For observers like us standing on a small planet billions of light years away, this slow cosmic drift is invisible. But our instruments let us sense it. We measure the faint glow of intra-cluster light, the spectral signatures of old stars, the heat of the gas still stirred by ancient jets. We see that the cluster's energy is balanced, its process is self-sustaining. Phoenix A, for all its size, does not dominate by force alone. It maintains the space where stars can rest and where galaxies can dream, turning the silence of gravity into a kind of cosmic equilibrium. Eventually, even that equilibrium will evolve. When the last stars of the Phoenix cluster fade, the cluster will still exist. Its black holes orbiting one another, its galaxies drifting in slow motion, its light reduced to faint radiation. Over unimaginable timescales, the black holes may merge, creating larger and larger singularities. Phoenix A could become one of the last active objects in that future cosmos, its gravity a lingering echo of the energy that once filled this region with light. The dreams of galaxies will become memories carried in space itself. And yet, even in that distant future, the principle of renewal remains. The matter drawn into Phoenix A will radiate energy as it falls, continuing the exchange that began at the universe's dawn. The photons released will travel outward forever, marking the last whispers of a cluster that once blazed with stars. The universe may cool and darken, but the patterns established here, the cycles of birth and rest, of light and shadow, will continue in their quiet form. The sleep of stars will become the dream of galaxies, and the dream will outlast the light itself. Phoenix A, at the centre of it all, will persist as witness. Its gravity will hold the remnants of the cluster in a loose embrace, its silence the final measure of time. And though no new stars will rise, their legacy will remain written in the faint radiation still crossing the void. The gentle glow of memory that endures after creation rests. The Phoenix cluster will continue to exist, not as a place of blazing stars, but as a structure of continuity, an echo of balance carried forward into the endless dark. The sleep of stars will not be the end, it will be the universe's longest dream. When we look into deep space, what we are really looking into is time. Each point of light is a message delayed by distance, each shadow an absence stretched across billions of years. The farther we look, the less we see of the present, and the more we see of what once was. In that way, astronomy is an act of witnessing history as it travels toward us. But when we look at something like Phoenix A, we are looking at a kind of paradox, a region defined by what cannot be seen. We observe light from the gas that surrounds it, radiation from the jets it creates, but the heart itself remains invisible. To see nothing and still understand it is one of the quiet triumphs of science. What we see when we look into nothing is not absence, it's the outline of reality itself. For much of human history, nothingness was treated as a mystery beyond comprehension, a void without structure. The night sky seemed to confirm that view, an expanse of black punctuated by stars. But what we have learned over the past century is that the darkness between those points of light is not empty at all. It's filled with fields, particles, and the fabric of space-time itself, stretching, bending, vibrating. The so-called void is an active medium, alive with potential. When we turn our telescopes toward Phoenix A, we're not staring into a blank. We're observing the distortion of that medium by gravity so extreme that even light cannot leave. The nothing we see is the most powerful something in the universe. The area around the black hole is not a place of silence. It's a region of extraordinary activity, where matter falls inward, heats, and emits radiation across every wavelength. To us, though, it appears as a dark patch, a place where light curves away or disappears entirely. That darkness is not a visual illusion, but a boundary of information. Inside it, the known laws of physics break down. We can describe what happens up to that point, but beyond it, our models fail. When we look into that nothing, we are looking directly at the limits of understanding. The darkness marks where knowledge ends and speculation begins, and yet, that limit is not discouraging. It's what gives the cosmos depth. The fact that some regions remain hidden is what allows science to move forward. The shadow around Phoenix A isn't just the absence of light, it's the presence of curiosity. Every attempt to measure it, every image of its surrounding gas, every calculation of its mass and spin is a way of outlining the shape of what cannot be seen. The nothing we look into becomes a mirror for our own need to know. When astronomers speak of observing black holes, they are really describing the act of inference. They track how matter behaves nearby, how gas orbits, how light bends, how jets form, and from that motion, they deduce what must lie at the centre. It's a kind of visual archaeology, reconstructing an unseen structure from the marks it leaves on its surroundings. In the Phoenix cluster, those marks are immense. Cavities in the X-ray glow, ripples in the gas, arcs of radio emission. Each of those features points back to the same cause, an invisible object too massive to be anything else. The fact that we can describe that object with precision, even without seeing it directly, shows how observation and imagination cooperate in science. Looking into nothing also teaches us humility. The space between stars, the gaps between galaxies, the darkness surrounding a black hole. All of these make up most of the universe. The luminous matter that we can see accounts for only a tiny fraction of what exists. The rest is dark matter and dark energy, invisible but measurable through their effects. When we stare at Phoenix A, we're reminded that our perception is limited, tuned to wavelengths that reveal only a sliver of reality. The cosmos is mostly made of things we cannot see, and yet those unseen forces define everything we know. There's a quiet beauty in that realization. The universe doesn't need to be fully visible to be understood. It speaks in patterns, in behaviors, in consequences. The nothing we observe around Phoenix A is filled with those signs. The gas swirling near the event horizon glows in X-rays. Magnetic fields twist and release energy. Space itself curves. Even the absence of light becomes a form of evidence. Each shadow tells us how strong gravity is, how fast matter moves, how deep space-time folds. The darkness is data. To look into that darkness is also to confront time on a scale far beyond human experience. The photons we detect from the Phoenix cluster left their sources 6 billion years ago. The structures they illuminate have changed since then, but we see them as they were, a frozen image of a past still unfolding elsewhere. In the deepest exposures, the sky becomes a tapestry of ancient events, each one long over but still shining. The nothingness between them is not an empty backdrop. It's the record of distance itself, the measure of how long light has been travelling to reach us. Even the quiet between signals carries meaning. In regions where no light appears, where the detectors record only background noise, there can still be faint imprints of structure, weak gravitational lensing, subtle distortions in the cosmic microwave background, the faint pressure of the intergalactic medium. Astronomers use these traces to map what cannot be seen directly. In doing so, they reveal that even the deepest voids are shaped by gravity, threaded by filaments of dark matter that connect galaxies and clusters like invisible scaffolding. The Phoenix cluster sits within that framework, not isolated but woven into the cosmic web. Its nothingness has shape, texture, and continuity. When people imagine looking into a black hole, they often picture falling, being drawn inward until there's no escape. But in truth, the experience is more about reflection than descent. What we see in that void is the limit of perspective, the point where our sense of time and space begins to fail. The nothing inside a black hole is not a place one could visit or stand in. It's a concept, a mathematical frontier. To look at Phoenix A is to see a horizon in the truest sense, a boundary beyond which the landscape of reality disappears from view, even though it continues to exist. This realization has changed how we define seeing. For most of human history, sight meant direct observation. To know something was to look at it, but astronomy has expanded that idea. We now understand that to see is to interpret, to gather signals across all wavelengths, to translate them into meaning. When we look into nothing, we are still seeing, just in a different way. The image forms not on the retina but in the mind, assembled from data and theory. The void becomes visible through understanding. The Phoenix cluster teaches this lesson vividly. Every observation of it combines information from radio, optical, X-ray and infrared wavelengths, stitched together into a composite that represents no single kind of light, but the sum of them all. The black hole's invisibility is surrounded by evidence of its presence, a sculpted halo of gas, arcs of star formation, the gentle pressure of heat on the surrounding plasma. When we look into that nothing, what we actually see is the shape of everything it influences. The absence is the outline of existence. It's easy to think of nothing as a destination, a final endpoint beyond which there's no more to know. But the deeper science peers into emptiness, the more layered it becomes. Quantum theory suggests that even the vacuum of space is not truly empty, but filled with fluctuations, temporary particles appearing and vanishing. The nothing between galaxies hums with virtual activity. Gravity and quantum mechanics both insist that emptiness is dynamic, alive with unseen motion. Phoenix A's gravity warps even that restless vacuum, stretching the fields of space until their energy changes form. The nothing we see is an arena of ceaseless transformation. Perhaps that is what makes it so compelling. When we stare at a black hole, we aren't looking at a void in the emotional sense. We're looking at potential condensed into its purest state. The absence of light is the presence of possibility, the visible mark of physics at its most extreme. Phoenix A, by its very invisibility, reminds us that knowledge begins where sight ends. What we see when we look into nothing is not despair, but structure waiting to be uncovered, order hidden in shadow. The darkness at the centre of the Phoenix cluster is therefore not an ending, but a boundary to comprehension, a line that invites us to keep moving toward it, even though we'll never cross it. It tells us that reality is larger than the part that shines, and that understanding comes as much from what we cannot see as from what we can. To look into nothing is to see the universe reveal its framework in reverse, the fabric, the depth, the continuity that light alone can't show. And so, when we turn our gaze toward that silent centre, we aren't seeing emptiness at all. We're seeing the architecture of existence shaped by invisibility. We're seeing gravity write its signature into light. We're seeing how the universe keeps its secrets in plain sight. Phoenix A's darkness isn't a hole in the cosmos. It's the place where everything converges. The visible, the invisible, the known, and the unknowable. What we see when we look into nothing is everything that remains. When all the numbers have been calculated, when the maps are drawn, when the images have been processed and catalogued, there remains something that cannot be measured. The quiet feeling that rises when we look at the universe and realise how small we are within it. Science explains the motions, the distances, the temperatures and the energy outputs, but it does not remove the feeling of awe. It sharpens it. The closer we come to understanding an object like Phoenix A, the more mysterious it becomes. Not because the knowledge fades, but because the scale of what it represents expands beyond comprehension. That expansion is what keeps curiosity alive. It's what we might call the soft gravity of wonder, the pull that brings our minds back to the stars no matter how much we think we've already learned. That pull has always been there. Thousands of years ago, people looked at the night sky and wondered what the lights were, what the darkness meant, what lay beyond sight. Those first questions were not so different from the ones scientists ask now. The tools have changed, the scale has grown. But the feeling of wonder is the same. It's the same impulse that drives an astronomer to spend years studying faint signals from a cluster 6 billion light-years away, and the same one that makes us stop and stare at the sky on a clear night. Knowledge doesn't cancel wonder. It feeds it. Each answer becomes a new horizon, a new question waiting beyond it. When we study Phoenix A, we're not just studying a black hole. We're studying the structure of reality, the ways gravity bends time and space, the mechanisms by which energy moves and matter organizes itself. We are looking at something that exists at the limit of understanding. Every observation reveals more, but also reminds us how much remains unseen. The more we learn about the cluster, the more it draws us in, not with noise or spectacle, but with quiet persistence. The black hole itself is silent, yet it commands the attention of every galaxy around it. Its pull is not only physical, it's conceptual. It teaches us that even in silence there is depth, even in stillness there is motion, even in darkness there is beauty. The soft gravity of wonder works in much the same way. It's not loud or overwhelming. It doesn't demand belief or awe. It simply draws us closer, asking us to notice. When we think about Phoenix A, when we imagine its jets, its surrounding gas, its enormous weight pressing on space-time, we are pulled towards something larger than explanation. The numbers are precise, but the response they generate is emotional, human. That feeling of scale, of standing on a small planet knowing there are structures out there that defy imagination, is both humbling and comforting. It tells us that we are part of something vast but coherent, something governed by rules we can learn, even if we'll never master them completely. The wonder deepens when we consider how our species, fragile and brief, has managed to uncover so much. Every photon that reaches our instruments has travelled across billions of years to find us. Every measurement we take is an act of connection across cosmic time. We build detectors, launch telescopes, and process signals with computers, all to listen to a universe that has been speaking long before we appeared. Phoenix A's light, or rather the light from its surroundings, began its journey when Earth was young. To catch those photons now is to catch a message written in gravity, carried on radiation, waiting patiently for our attention. The wonder is not just in what we see, but in the fact that we can see it at all. The scale of that connection is hard to grasp. The energy released by Phoenix A's jets equals the combined output of trillions of stars, yet it reaches us as a faint trickle of photons, barely distinguishable from background noise. We take those faint signals, amplify them, compare them, interpret them, and from that effort we extract meaning. The result is not just data, but insight. We see how the cluster breathes, how energy flows, how gravity shapes everything around it. From the smallest variations in light, we reconstruct entire histories. It's an act of translation between silence and understanding. That, too, is part of the soft gravity of wonder, the way the universe invites us to listen closely enough to turn faint whispers into knowledge. What we learn in the process is that the universe is not indifferent. It's vast and impersonal, yes, but it follows laws that make order possible. Those laws don't favour us, but they include us. The atoms in our bodies obey the same physics that govern Phoenix A. The forces that hold galaxies together are the same ones that hold us to the Earth. The connection is not metaphorical, it's literal. Every discovery in astronomy reaffirms that continuity, reminding us that we belong to the same fabric as the stars and the void between them. That realization carries a kind of peace. We are not separate from the cosmos we study. We are its product, its expression, its way of knowing itself. When we look at images of the Phoenix cluster, the glowing arcs of gas, the faint halos of galaxies, we are seeing something that exists beyond human timescales. It will continue to evolve long after our species is gone, and yet, in studying it now, we've become part of its story. Our observation changes nothing about the cluster itself, but it changes us. We learn to think in longer terms, to imagine processes that unfold over billions of years, to see beauty in patience and proportion. Wonder doesn't end when the facts become clear. It begins there, in the space between comprehension and imagination. The soft gravity of wonder is also what makes science a human act rather than a mechanical one. It's not just about collecting data or verifying equations. It's about the feeling that accompanies discovery. When a researcher first sees the faint outline of a cavity carved by Phoenix A's jets, there's a moment of quiet recognition, a sense of connection to something larger. The data are numbers, but the experience is almost spiritual. It's the same feeling that guided the earliest astronomers when they mark the motions of the planets, the same one that led Einstein to imagine space-time bending around mass. Curiosity is gravity for the mind. It pulls us toward the understanding, and the closer we get, the stronger it becomes. That pull doesn't fade with distance. Even for those who never study the cosmos professionally, the wonder is still there, waiting in the night sky. You don't need a telescope to feel it. You only need to look up and remember that every star is a story unfolding across time, that behind each point of light lies complexity beyond measure. Somewhere among those lights in a distant cluster, Phoenix A continues its quiet work, balancing creation and destruction, shaping galaxies, teaching us about gravity's patience. The light from its surroundings will continue to travel long after we're gone, reaching other worlds, perhaps other eyes. Wonder itself moves forward, carried by the universe it seeks to understand. There's a kind of symmetry in that thought. Just as gravity binds galaxies into clusters, wonder binds minds into curiosity. It's what turns observation into reflection, and reflection into meaning. The universe doesn't require our attention, but it rewards it. Every time we look outward, we discover that the same order exists within us. The same patterns, the same forces, the same quiet persistence. Phoenix A's enormity reminds us not of how insignificant we are, but of how connected everything is. To feel wonder is to feel gravity's softer form, the one that holds ideas instead of planets, that shapes thoughts instead of stars. Eventually all light will fade. The stars of the Phoenix cluster will die, the galaxies will drift farther apart, the universe will cool towards silence. But wonder, as long as there are minds to feel it, will continue to rise. It doesn't depend on brightness, it depends on awareness. The soft gravity of wonder isn't extinguished by darkness. It grows stronger in it. In the quiet, it draws us to look again, to listen, to ask, to understand. That pull will never end. And so, as the last photons from Phoenix A's ancient light reach us, they carry more than information. They carry continuity. They remind us that in a universe where even light can vanish, curiosity endures. The cosmos expands, stars sleep, black holes wait, and somewhere, someone looks up and wonders. That act, the simple, patient wondering, is the gravity that keeps us connected to everything. It is soft, but it holds the weight of infinity.